So today we have to start the PN junction, I think. PN junction diode. A diode means a two-terminal device. So earlier we used to have, before the invention of diode, we used to have something called cathode ray tubes. And in that case, we used to have the triode also, tetrode also, pentode also. Those were the three terminal of 4 or 5 terminal device. And in the television, I mean, earlier they were using the CRT tubes. Now, once we got this, the semiconductor came into being, and when this diode was invented by the Bardeen, Shockley, and all, then after that, the design pattern changed, and not only that, the size also reduced significantly. So the first, you can say, the calculation engine that Charles Babbage designed was, I think, few-story building, and he was not able to complete that as well. And the entire capacity was something kV. So imagine a building size of a machine can only do calculation up to some kV. And now today, on a tip of your nail, you can probably store few terabytes. So that progress we have seen over the last 70, 80 years. So we'll start the PN junction diode. So a diode is basically a two-terminal device, okay, which act as a switch. So it is a two-terminal device So the role of switch is either on or off, right? So we have on state and we have off state. So that is the purpose of a diode. These are very thin layers. How thin it is up to few micrometer thickness. In that micrometer, we have multiple layers. Okay. So if I draw micrometer, okay, I can't draw. Even if I draw this line, this is in millimeter, I think more than millimeter. So you can imagine that it is millimeter. If I divide this into 1,000 parts, then I'll get a micrometer. And within that micrometer, we have some nanometer range of layers. So it is almost impossible for you to visualize what exactly is this diode. But for the sake of illustration, we are going to create a PN junction diode. So what we do is we take two different types of semiconductor, which is extrinsic semiconductor. So you may take a P-type semiconductor and N-type semiconductor. And in the P-type, what we have in the majority carrier. So the majority carrier will be here. Majority carrier is going to be holes. But every majority carrier will also have the minority carrier, right? So the minority here will be
electrons.
Electron. Very good. Similarly, in case of N-type, it will just reverse. So the majority carrier will be electron. So the minority will be holes, right? Holes. So now when you combine the junction, now of course you cannot stick by adding some glue. It is done through various process. So it can be done through the heating process where you fuse the boundary of the two medium and it becomes a single device. So if you join these two together, the P-type and N-type, so the moment you bring the two types together, So in p-type, how we represent the p-type, by the way, if you remember that I have told you, okay, in how we represent p-type. In the p-type, what we have? The lattice atoms will be negatively charged, right?
Yeah.
Yes.
So I'll draw few layers. I mean, one more layer. And within this layer, on the p side, these layers are like, these are fixed atoms. You cannot move these atoms. So are these carriers or only charge? So what I'm
Just
representing is carrier or charge.
fixed charge, not
These are
carriers.
fixed charge. Now to represent the carrier, we have to draw a hole here. So tiny dots are like carrier. And here we have electrons as a carrier. You can draw as many layers as you think of. And because the dimension of atom is in angstrom, so you can imagine that 1 micrometer will have how many angstrom? Correct? So typically, even if you take 1 micrometer thin a diode, you can imagine there are 10,000 layers of atoms. So that's a huge layer, right? Out of 10,000, I have shown you few, just 2 and on the right, 2 on the left. You can keep on drawing. Okay. Now you can see there is no battery attached. Nothing is attached. Okay. So what will happen? So there's a process called diffusion. So whenever there is a difference of concentration, then diffusion occurs, right? So you can
Yes.
see the holes are excess on the left in the p side, right?
Yes.
So we have excess of holes on the p, but we have excess of electron on the n side. And these excess of holes and electron will start flowing and will create a current. And because this current I am not creating out of some battery or some field, even the field is intrinsic field, or you can say internal electric field, which we don't know. But they will flow automatically on the two sides of the junction. So electron will go which side? So the majority carrier will move on the
Okay.
opposite side of the junction, isn't it?
Yes.
And the flow of a majority carrier on the opposite side of junction is called diffusion current. What do you call?
Diffusion current.
So diffusion current is due to the difference of concentration. So flow of charge by virtue of difference of concentration is called diffusion current. So we can say flow of charge by virtue of difference of concentration across the junction is called diffusion current. So I have talked about diffusion current in current and electricity also, but here there is an actual application. So diffusion current is something which occurs on its own. You're not supposed to connect any battery or something. And these are like short-lived current, which means the moment you make the junction coming closer, the diffusion current will occur for nanosecond and it's done. So in the nanosecond, all of this event will be over. But while crossing the junction, the electron and the hole will meet and will annihilate each other. Okay. So I'll just mention this. So while crossing the junction, electron and hole will meet and annihilate terribly spring annihilation each other. So they will annihilate each other. Now, as a result of annihilation, what will happen? It will release some energy, and it is quite possible that if this diffusion is very interesting. Sometime using this diffusion process, we make a kind of forced diffusion. There is something called forced diffusion, and this forced diffusion is used to create the LEDs. Okay, so light emitting diodes are nothing but the a mechanism by which we create this diffusion artificially, and when the electron and hole meet, they kind of, based on the energy gap, they release the energy in form of photon. So that is how they emit the light. So it is again the same thing, the annihilation process, or you can say excitation and de-excitation process, or as you can compare from the Bohr's theory. Okay. So when they cross each other, they annihilate, and it's like they get lost. So no charge will be available in the region of annihilation. So they eat up each other. Now the question is, if they eat up, then what they become? So the answer is they become back to a bond. So they create a bond actually. So breaking of covalent bond creates the electron hole pair, and recombination again recreates the bond. You can think that way. So now after the annihilation process, how it will look like? So the two junction, make it bigger. So after this process of annihilation, few layers of atoms. So let's say maybe 10 layer of atom this side, 10 layer of atom this side. I'll just do it by doing a few lines. So the atoms in these regions, so this is P, this is N type. In the P type, we have minus here, right? So these layers has participated in the annihilation process, or you can say diffusion process. Change the color. So in this region, what do we have? Do we have charge carrier, or do we have only charge?
Only charge.
Because the carrier has been lost. So now there is no carrier left. So we say that this region is deprived of charges. This is depleted of charge. Depleted of charge carrier. And because they are depleted of the charge carrier, there is a name for this kind of a region in world of semiconductor. What do we call this region? So what do we call it? We call depletion region. Okay. So every PN junction diode will have depletion region. Yes or no?
Yeah.
That's natural because the diffusion will occur. We cannot stop the diffusion. But the question is, will this diffusion occur forever, or will it stop after some time? What is that? It will stop. If you think carefully, a charge deprived region will act as a dielectric. So this region becomes a dielectric because there is no charge carrier. And if you think of a capacitor with a dielectric, so the role of depletion region is exactly the role of a capacitor. So it will behave as a capacitor. Now this is like a, so this is called, there is a name for this. Diffusion capacitance. We represent by CD. So this act as a diffusion capacitor or diffusion capacitance it will have. So a depletion region act as a capacitor. You can think this as a negatively charged plate. So you can think as a negatively charged plate. Difficult, I should have done some with that, but nevertheless. And this will act as positively charged plate. So can we imagine some sort of electric field inside?
Yes.
The field will not be exactly uniform, but because the layer is so thin that okay, there is no problem even if you consider as a uniform electric field. So we do have electric field between the region, and therefore, while going from the negative to positive plate, the potential will rise or increase, decrease. What will happen? So if we draw a graph of potential versus X, then you can see the potential will rise while crossing the depletion region, isn't it?
Yeah.
Because you're going against
Yes.
the field, so potential will rise. So this difference of potential that they create, this potential difference, which they create, this is called VB, and the VB is called barrier potential. So you can imagine it's very simple. Barrier potential is like a potential which is always available. Like there is always a kind of opposition. Now what will happen? Think carefully. So the field is left. Now who is the which charge is majority carried in the left side? Hole.
Holes.
And what is the majority carried in the right side?
Electrons.
Imagine there is a field. So there is a very strong field in the region. If a hole will try to enter this region, it will be thrown back by the field, yes or no?
Yes.
Because the field is also left. So now for this hole to enter this region is a challenge. Okay. So unless the kinetic energy carried by this hole is not exceeding the barrier potential energy, I mean, you know how to find this energy, right? So for any charge, the difference is how much? Charge into potential difference, VV, correct?
Yeah.
So how much energy you need to have to cross this junction? The energy required to cross this junction will be the charge, or you can say E into VB, isn't it?
Yeah.
Yes.
So unless you're not giving this much charge, sorry, this much energy, is it possible for the hole to cross the barrier potential of this depletion region? So it will go, it will enter inside, and if it is less than this, it will still return back. And same will happen with the electron. If electron is trying to enter from the right, if you enter here, the force will be which side? Because the field is left, charge
Opposite.
is negative, the force will be left only.
Yes.
So any entering electron will experience the same force on the left, and every hole will enter to experience the force on the right. And you can see in each case, it will bar the extra carrier to enter this region. It means as long as the barrier potential, and you can say there's something like a thermal energy. Okay, so while in the diffusion process, they do go across each other, but while crossing each other, they create a depletion region. They create some sort of a dielectric capacitor, and that dielectric capacitor will create its own internal field, which will even further prevent the process of diffusion. So diffusion will not occur forever, right? We can understand this. It will eventually stop. Understood? So
Yes.
every process of diffusion is going to stop eventually. And that is the, I mean, you can say it will attain some thickness. The thickness will be in a nanometer scale. Now the question is, what will affect the thickness? Like how the doping and versus thickness will occur. So imagine if we have a highly doped semiconductor. So in a highly doped semiconductor, a single layer will contain more number of carrier, isn't it?
Yes.
And if the number of charge is more, can we say the charge density will be more? The sigma will increase.
Yeah.
So as doping will increase, sigma will. So for the diffusion
Great.
capacitor, can we say the surface charge density of the diffusion capacitor will be proportional to the doping? Kind of. I mean, it's like analogy. We are trying to draw the analogy. See, I mean, we are trying to learn the entire thing through the concept of electrostatics only. The electronics part is something quite different. So in electronics branch, what happens? We study through the application, that if you want to design something, so there we go by specification, but we want to understand the fundamentals, then we can go to the physics. So semiconductor is mostly commercially, commercial device in which everything is predetermined. Okay, so you know that what kind of application you're going to use. And for the given application, we design it's a reverse engineering, you can say. Okay. So now I'm saying that the surface, okay, write it down. It's easy for me. Just a moment. The surface charge density of a diffusion capacitor will be proportional to doping, right, of PN type. So tell me, like, as the doping will increase, what do you expect? That depletion region will be thinner or thicker? So what will be the effect of doping on the depletion thickness?
Sir, it will become thicker.
With more doping or less doping?
It will be thinner, I guess.
It will be thinner
Because the field will become stronger. So
very strong, yeah. So even a thin layer will be powerful enough to stop the diffusion, right?
Yeah.
Understood? It is clear?
Yes. Yes.
So more the doping means more stronger the field. So doping increases the field. Now that is also very interesting. Should we keep on increasing the doping to make the depletion region as small as possible? Is it dangerous?
Yes.
Because if the field becomes really powerful, it may create the dielectric breakdown. So that's also dangerous. I mean, we have to be very careful. See, design is, the diodes are so sensitive device that everything having limitation. So whatever you want to do, there is a limitation. Okay. Too much doping is also dangerous. In fact, we do create that too much doping to create a specialized diode, which we are going to learn, called zener diode. Okay. And there, this idea of extreme doping will come into picture, that we want really to break the junction, and by breaking the junction, we create some sort of voltage regulation. So we'll come to that. That is the very important part of this topic, because a large number of questions you will see from the last years, they have been asking questions from zener diode. Okay, but the zener diode is really simple to understand. So the surface charge density of diffusion capacitor will be proportional to the doping, isn't it? So more doping means is stronger E in the depletion region.
Yes, sir.
Okay. And if we have the stronger field, then diffusion will stop very soon and the thickness will not grow much. Okay. So I hope this is clear to all of you. So the barrier potential is clear. What is barrier potential? Okay. So once we have this PN junction, then there is a circuit, because in circuit we are not going to draw something like this. But there is something really interesting here. You know what is interesting? A barrier potential will stop which carrier? Majority or a minor carrier? Or both?
Majority.
So it is trying to stop the
Support the
hole,
minor carriers.
but it is going to favor the electron, isn't it? And it is going to favor the
Yes.
hole on the other side. because the moment it will enter, it will pull it back in no time. And the moment this will enter, it will pull it back. So in a way, when you kind of oppose the majority flow, you support the minority flow. Okay. But the minority carrier, because see, the concentration of minority is so small that it is almost in the range of nanoampere. So a nanoampere current will make no sense. I mean, we need even a very extremely sensitive device for its measurement. But once you increase the, okay, now we'll come to the biasing. So don't worry, one by one. So now we have the circuit symbol. So to solve question, we cannot draw this box diagram. Rather, we draw a triangle. It is like arrow. Arrow means the flow of current direction. Okay, so how current can flow? Towards the right only. So if I draw a diagram like this, it means the direction is right. But to create a diode, we do have a barrier. So we represent the barrier by the symbol, the vertical line. You can think this way. And the vertical line is called cathode. And this is called. So this is our negative terminal. And this is our positive. Positive means high voltage end, and this is the low voltage end. And then you draw a line. This is your two terminal device. So this is called the two. Now we will have two types of diode, real and ideal. So we have a silicon diode, I mean real diode. So a real diode and the ideal diode. So the real and ideal differ in what? Barrier potential. So we assume that the ideal diode will have the zero barrier potential. This is the assumption. But the real will have barrier potential. Okay. So how to represent a real diode? So in the real diode, they will mention the name of the diode also. Let's say they'll put silicon here or germanium. So generally we use the silicon and germanium. So let's say I write silicon here. So you can convert this into an ideal diode with a barrier potential. Now the question is how to represent the barrier potential. So barrier is like opposition. Okay. So to represent the barrier potential, you can draw a battery of reverse polarity and you can name it VB. And now this is the ideal with a battery. So this is equivalent of these two symbols. For silicon, the barrier potential is used is 0.7 volt. And for germanium, they will give you the value. I mean, no need to worry. But for germanium, anyone knows the value of germanium? It is 0.3 volt. So germanium is also used for the expensive one, and we do use the silicon. Depending on the availability and the uses, we can use silicon or germanium. So now we have to understand the concept of biasing. So what is biasing? Biasing means simply connecting the battery. That's it. So we have types of biasing. We have forward bias, forward biasing, and the reverse biasing. So any PN junction is said to be forward bias if the P is attached to the high voltage and N is attached to the low voltage. So for example, if this is minus 20 volt and if this is minus 50 volt, what we can say is it forward bias or reverse bias?
Forward bias.
Forward.
So it is forward bias. So the value doesn't matter. What matters is the relative value. If the P is at a high potential, I'm saying high, I'm not saying plus. Positive is not required. It should be high potential. And the N is at low potential. So a high to low will make it forward bias. And once the diode is forward bias, you can replace by a short circuit. So it is short circuit. So if it is ideal, then short circuit. If it is real, then short circuit with a battery, isn't it?
Yes.
Okay. And what is reverse bias? Just reverse the process. That's it. So in the reverse biasing, the positive terminal should be at a low potential and the negative is at high potential. So it is reverse bias and it will act as, in this case, open circuit. So you can convert into circuit and just make it open and close. You can do the problem. So that's a simple biasing technique. There are some questions that you will come across only based on this idea of biasing. Let me show you some of the examples. So if we have a, okay, we'll start with the, if I don't mention silicon and germanium, you have to assume the by default ideal diodes. Okay. So we
Sir,
have
can you just switch to the previous slide? Okay, done, sir.
just okay. So I hope this is clear.
Yes.
Okay. So now how the question look like? So they will give you a question like this. There are two diodes. And there is a potential. And these are ideal diodes. Okay. And because this is the ideal diode, if you can say D1, D2. So this is high potential. This is low potential, right? So which diode is forward bias? D1 or D2? So D1 here is,
D1 is
D1.
forward.
D1 is forward.
and D2 is.
Reverse.
So you're supposed to simply remove the, see if it is forward bias, simply make it like a wire. It is short circuit. And this is like open circuit. You cannot do anything. So current will flow through which branch? Only top branch.
R1 branch. Yes.
Yes, sir.
So you know how to solve the question. So I equals to V by R. That's it. Okay.
Yeah.
All right. So imagine that this question is given in a different way. This is 10 ohm. This is D1. This is 20 ohm. And now here, the battery is replaced by a pulse generator. So we have pulse generator. So these are called waveform. Okay, waveform means you have some alternating waveform. Okay. And let's say they may give you graph of the waveform. So the voltage versus time is like this: positive, negative. Okay. So this is the waveform, and you can think this as plus. This is yeah, fine. So the value is constant, but it is alternating. That's the whole idea of waveform. And okay, I'll do a better diagram to make it easy for you to understand. Okay. So imagine in the first instant when you start, then the positive part of the waveform is incident. Okay, so let's say left is positively when high potential and right is the low potential. This is how you start with. Imagine. Then in the first case, which one of the diode will be active and which one is the open? So the first stage for the first interval, you can see D1 is going to be
D1 will
active.
be, yeah.
So the current will be how much? How the graph of I versus T will look like?
V naught by
V naught by
10.
So we can also decide the direction of current. So let's say this is the positive direction of current, and this way is the negative direction of current. I mean, of course, they will give you some better convention. So now tell me, for the first instance, current will be right or left?
It means origin of current.
Yeah,
Left.
current will go towards left or towards right for the first step.
We go clockwise.
For the first, it is left, no?
Yes. Yes,
Because
sir.
D1 is active, D2 is open, and
Yes,
the
sir.
value will be how much? V naught by 10.
10.
So this is V naught by 10. But for the second one, what will happen?
Directional frequency.
It will be V naught by 20, right?
Yeah.
It will be like lesser. So it will like graph will be like this. So you will be asked to draw the graph mostly. The waveform will be given to you and you're supposed to draw something like this. Understood?
Yes.
Yes.
Okay. So how questions actually are made in look at this. So they give you like something like this. A diode and a resistor and this is called output voltage and this is your input voltage. Okay, and let's say if I say this is silicon and then the graph is this is 2 volt minus 2 volt. Okay, so this is like high voltage, this is low voltage, and let's say this is plus, this is minus. Okay, so how the graph of output will look like? Any guess? So silicon means what? We have to take the barrier potential as 0.7 and you want to plot the graph of the V output versus time. And what is given to you? The V input. V input is given as a pulse. So when it is 2 volt, the D will be FB or RB?
FB.
FB. FB.
FB. So D is going to be FB, right? So it is forward bias, correct?
Yes.
Yeah.
So you will get the entire voltage 2 volt. Okay. Because it is no, but there's a problem.
So
The-
VB.
Opposite
Yeah.
barrier.
So the barrier will lose. So what we'll get is 1.3 only.
1.3.
Yeah.
So it will remain 1.3 forever till you make this. But the moment to become negative, it is a reverse bias. Now the
Yeah.
question is, this is 1.3. In the reverse bias, it is open circuit. So what will be the potential across R? That's interesting. See, there is no current, no?
Zero.
So voltage across R will be depending on IR. So V naught is basically
Zero.
IR, and because there is no I, so the answer is 0. So this is 1.3, then 0. Then again, graph is clear to all of you guys. Tell me.
Yes, sir.
Now the question will come like this. See, output is basically the voltage across the resistor is the output, isn't it? And now the input waveform is this of height, let's say 5 volt. How the output will look like? Tell me. So for the positive cycle, the diode will be which bias? Reverse or forward?
Forward.
Forward.
But there is a
Forward.
problem. It will not start connecting unless you're not crossing the barrier.
Barrier.
So 0.7 is the barrier, right?
Yes.
So up to 0.7, you can say height, this height. Let's say this is 0.7. There is no current. Understood?
Yes. Yes, sir.
So how the graph will look like? I mean, there is no current. There is no current. So up to 0.7, nothing will happen. Okay. And then once you cross it, the current will start. So it is like you have chopped the graph, isn't it? You can see
Yes, sir.
the graph is like a chopped graph. And how much it can go up to?
4.3. 4.3.
So this is called clipping. You have clipped the graph, clipping. So there is something concept called clipping and clamping in diode. So you have clipped. So barrier will clip that part, and then the output will start only from once you cross the barrier value, right? Because before the barrier it is still 0, isn't it? Before the barrier current is 0. Yes or no? Tell me, guys.
Yes, sir.
So only when the input voltage will cross the barrier, then current will start connecting.
Yes,
It's
sir.
clear? Okay. And then what will happen the next cycle? If it is
It will
open
stay at
circuit, then
0.
it is again 0.
Reverse.
So it is 0 for greater interval, right? Not
Yeah.
only half. It is C. This is the interval of 0.
Yes, sir.
Because this is a big graph. So you can see the gap will be more. Then it again. So do you realize the graph?
Yes, sir.
Okay. So these kind of question is very commonplace. I mean, you will come across the waveform plotting questions very often in the JEE-Mains. Okay. So this was the PN junction diode, the forward bias and the reverse bias. Okay. So if you want to solve more question, or is it sufficient? You can solve some of the JEE-Mains question quickly just to get some confidence. So open the JEE-Mains, I mean that booklet you all have.
Yes, sir. Open.
Yeah, please open.
Which question?
Just let me. Yeah, you can see any question like question number 15, page number I think 484. Page 484. 484. Can you see that?
Yes, sir.
Yes, sir.
Can you see the question number 15? 11 January 2019, I think.
Yes, sir.
Yes.
I mean, that's very simple. I mean, you can solve it. Done? And read carefully. The forward resistance is 50 ohm. It means when you replace it, you cannot make it short circuit. You have to make a resistor of 50 ohm. Understood?
Yeah.
So forward resistance is finite value, but the reverse resistance is infinite because it's open circuit. Understood? So every real diode in forward biasing offers some resistance called the forward resistance, RF. But anyway, I mean, see, even if you don't know much of his semiconductor, you can understand by common sense what I'm supposed to do. So which one will conduct here? D1 or D2?
D1, sir.
D1.
So D2 you can, the entire branch of D2 you can throw out. Because that branch will not offer the current. So you can just throw it out. And then replace D1 by 50. So this is 200 by 200 plus 100, 300 and by 6. Oh, you got it. 6 by
6
300.
by 300. 1 by
How much?
B.
B option.
B option.
0.0.
Oh my God, that's very difficult question. Solve question 19. You can see there 19. You can see.
Sir, if they haven't specified real or ideal, we have to consider
No,
it as
silicon. It's written silicon diode. 0.7 will come
okay.
because in NCERT they have given the value for silicon and germanium, and you're supposed to remember the answer. So that is why it is 2.3, na? 2.3 by 200 something like this. 2. Whatever. Yeah. Silicon is 0.7. The reading of the emitter. So what is the reading of emitter? 3 minus 0.7. 2.3 by 200, right?
I guess C.
Yeah, of course. It is
So
C.
it would have some standard value of that forward resistance also, no?
But they, okay, if it is there, they'll mention it. If it is not given, it means you are not supposed to assume.
Okay.
There are many ifs and buts. Okay, I mean they give the value. You have to be smart enough that what to use, what not to use. If it is not given, so the standard value, no. The resistance cannot have the standard value. I'll tell you why. A diode will have any semiconductor device will have the variable resistance. Okay. And it depends on the biasing. How much is the biasing?
Yes, sir.
Done? I hope so.
Yes.
Rest is zener diode. So let me find some question that you can practice and just gain some more confidence. This is again zener. Mostly a zener. See, you can see there are so many zener diode, right? Let me see the waveform question. Waveform. This is you can see there are many waveform, right? Yeah, there is a question here. Yes, question number 18. Can you see the question number 18?
Yes.
Yes.
Okay, so try to read this. So germanium silicon diodes start conducting at 0.3 and 0.7. Yeah, that's fine. So in the following figure, if germanium diode connection are reversed, the value of V0 changes by. So tell me what will happen. So in the beginning, in the question number 18, in the beginning, which diode we have to take forward bias? Because see, both are forward bias. But the one with lesser barrier potential, we have to take the forward bias. Understood?
Yeah.
So in the starting, germanium will become short circuit with 0.3 volt. Second, we have to keep as open. Why?
Can I explain why?
Yeah, because the moment you have germanium, the potential across silicon is depending on germanium, right? See, I have become, open circuit, short circuit. So I will dictate the potential, right? So I will make sure that potential remains 0.3. So silicon will never become forward bias. Just, I think you're not getting it. It's a simple. This is how much? 0.3. So once this is open, because it's a lesser value, this gate will open first. But once the
yes.
gate will open, the voltage across this will be depending on this, no?
Yes, sir.
Now this will dictate the voltage. So this is how much? Only 0.3. So
Ah.
silicon will never get 0.7. So barrier will never cross, isn't it?
Yes.
And
Yes,
that
sir.
is why this germanium will dictate the initial current, and so the voltage across this. Clear?
Yes, sir.
So voltage across this will be how much? 12 minus 0.3.
0.3, 0.7, 11.
And then later on it will become 12 minus 0.7.
Ah.
Because once you reverse the germanium, it will never become forward bias. So silicon will become.
0.4.
So 0.4 is the difference, right? Is there any option like this?
Yes, sir. D.
So you can see all question you can do mentally. I want to see the option. Where is the option? Yeah, we do have option. D. Understood how to solve question?
Yes, sir.
So this is, yeah, solve question number 21. That is based on the formula, the ionic mobility. Solve 21. So what is the connectivity of a semiconductor sample having electron concentration? So Ne is given, NH is given, mu is given, everything is given. So what else you need? You need nothing. You just need a formula. Which formula you know? 21 formula?
Mobility one.
Sigma equals to mu E Ne plus
Mu H N H.
all into. Okay. I think everything is given in the question. Yeah.
Sir, I don't understand the previous question fully.
Which the germanium silicon?
Yes, sir.
Okay, just a moment. Okay. So tell me which part, like the potential part.
Sir, as in the part where if germanium, like if it first allows current through it, it won't allow silicon to become
Because
anything
see,
other than.
because if you have two things in parallel, let's say there are two things in parallel. So let's say we have a battery with internal resistance. There is a pure battery. E1, R1, E2. So what is the potential across E1? This is a pure cell without any internal resistance. So the voltage across this will be E2 only.
Yes, sir.
So the voltage across these two terminals is going to be E2. So this will also net get E2 only.
Yes, sir.
Here there are two caps. I mean, there are two diodes, one with 0.3, one with 0.7.
Okay. Yes, sir.
So which one is the smaller one?
Sir, the 0.31.
It means which one will get close first? Which one will
Sir.
start? It is like you activate the path will start connecting. So the one with lower value will start the path.
Yes, sir.
Once you activate the path, it is like a conductor. You can think this as a battery of value 0.3 like this.
Okay, sir.
Now, once we have a battery of 0.3 volt, silicon will also get dictated by this only.
Yes, sir.
And therefore, silicon will never get activated because you will only get 0.3.
Yes, sir.
And once you are getting only 0.3, what will happen? It remains open circuit.
Yes, sir.
So the voltage across this will be how much? 12 minus 0.3 if you just walk the path. This is
Yes.
0 volt. This is V0. So voltage across this is actually this voltage, right? You can do circuit. But later on, when you reverse the germanium, what will happen? It is reverse bias.
Yes, sir.
Now silicon will get a chance at least to be forward bias.
Yes, sir.
So now it is 0.7 volt battery. So the new potential which you will get across will be how much? 12 minus 0.7.
Yes, sir.
So question is how much V0 changes? So what is the change of V0? Tell me.
0.4.
So that's the answer.
Okay, sir.
I hope this is clear to all of you.
Yes, sir.
Yes.
Yes, sir.
Okay, so tell me guys for this answer. Okay, you are solving, I think, question number 21, no? Got the answer?
So just a second.
Just a formula. Don't waste time. Calculation should be accurate and fast also. So for every theory, if you keep on solving few questions, that will strengthen your concept. So that will make sure that at least you're getting some marks in the examination. Okay. Done?
Yes, sir.
Okay. Which answer? Option for
Sir, A.
A. Darsh.
No, sir, I was doing the previous question.
Previous. Okay.
Yes, sir. Got it.
What you're getting?
Option A.
1.6.
1.68. No?
Yeah, 1.6.
Fine. So can we do something more or shall I go to the next concept? Let me just check. You can do the question number this also, right? So it's a similar question, I think. 27th question. '27th. So anyway, now the last 2-3 years they have asking good questions. Earlier it used to be very simple. So let's go back to some more theory. As we add more theory, we can solve more questions. Okay. So diode as a rectifier. What is rectifier? What is rectifier? Tell me.
No idea, sir.
It is a device which converts sinusoidal waveform voltage current into what? Unidirectional waveform voltage. Correct. Simple. You rectify. So the requirement of most of the device is a DC value. Okay, you want a directional current. You want something only flowing in one particular direction. You don't want the reversal of direction. So what happens if you're using a small device, a handheld device in which you can buy a battery, then it's okay. But imagine that you want to employ the power supply to the household or to the industry to run the electronic device. What is the biggest problem? The device will not work because the current will keep on swinging from right to left, left to right, isn't it? So you always want to make the current flow unidirectional, one dimensional, not right, left, only right or only left. So that is kind of a requirement. But you want to do it with the help of a power supply. The household supply is what? It is alternating AC. So it's a sinusoidal. So we do get the sinusoidal supply. So the problem is this kind of supply is not good for the electronic devices. So we need a device which can make sure that it can only flow in one direction. So we call it rectifier. But you won't get a DC value, you will get a fluctuating DC, or you can say simply unidirectional value. So to make it DC, we have to add one more layer to this device, which we call filter. So we'll come to that. So first of all, we'll see the device is a rectifier.
Sir.
Yeah.
So we get DC of variable magnitude.
Correct. So we will try to make it again constant by through some other mechanism that's called the filter mechanism. Okay.
Like a charger contains these two devices.
Pardon?
The charger for laptops.
They contain both. They contain rectifier with filter circuit. But we are going to study separately. We'll study first rectifier, and then we'll attach the filter to the rectifier, and then we'll see the overall purpose of it. So in the communication, this is the most essential part, because in communication, what I'm saying is a sine wave only, right? And with the help of rectifier, we can filter out the message from the carrier wave using a method called peak detector, which is employed using the rectifier and the filter circuit, and that is called a demodulator in commercial language.
Okay.
Just a minute. Okay, so how many types of rectifier we have? Types of rectifier. So there are two types of rectifier. This is called half wave rectifier. This is the full wave rectifier. So we'll design both of them one by one. So we'll start with the so let's say we have an input signal. The input signal, you can think in terms of communication, it's easy. So we have an input signal which is completely sine wave. Okay. So there are many ways in which you can design it. So the way we are going to design is using transformer. So let me tell you how to draw transformer in a circuit. So to draw a transformer in a circuit, we draw two coils, the primary. Oh, I'll put on next page or this page. So we have a coil, let's call primary coil. And here we have the AC input. At some instant, this will be plus, this will be minus. This double line is for the coupling. So the primary coil is coupled with secondary coil. Okay, so you can join the primary with secondary. And then we attach a diode here. We are going to assume our diode as ideal one, because we just want to understand the rectification, not the answer, exact answer. And what you can do next is you can make it you can ground it, you can make it grounded 0 volt, and then you can draw a separate resistor across which you can going to find the potential difference. So the output we are going to derive from here. So whatever current that will flow here will give you the output voltage V equals to I naught R. So this is how you can design. It's very easy, not at all difficult. So this is the primary coil, secondary coil, coupling, and all those things. So we have the input voltage as a sinusoidal. So what happens that if we have the positive cycle coming here, this will be positively charged, this is negatively charged. So the D will be forward bias or reverse bias? Tell me.
Forward.
What is the biasing?
Forward.
So for the positive half cycle, it is forward bias. So a current, a secondary coil will have a current here. So a current will be established. And the same current will go eventually through the resistor. Okay. And that is how the voltage will be obtained. I mean, not I dash, you can assume. Maybe some current will go here. So you can just open it. This is just a way of showing. You can just open it and we are done. So what you're getting for the positive half cycle, there is an output here. So we do have the similar output. What about the negative half cycle? The same D will become open circuit, reverse bias, right?
Reverse biased. Yes.
And because it is reverse bias, so nothing can flow. So no current will be induced in the circuit. And therefore nothing will go through the R also. And therefore what we get is, you get nothing.
Sir,
So yeah.
sir, why are we grounding the other wire?
We don't want to create another circuit or another path actually. So grounding is a convenient way to avoid any further leakage. Okay, so everything will be there only. We just have only one path. The other path is 0 volt. So this will give you the reference line. This is like a reference. So a reference means you can compare whether it is high or low. Okay. If this is 0,
Okay.
if this is 0, this is also 0.
Yes, sir.
So now anything positive will make it forward bias.
Yes, sir.
But if it is non-zero, then anything is not forward bias. You need to understand, no, if this is, let's say 5 volt, then this must be more than 5.
Yes, sir.
So that's why we keep it 0, so that anything positive will make it forward bias. Okay.
Okay, sir.
Now, if you plot the graph exactly below it, so the output will get the positive half cycle, but you will not get the negative half cycle, right? So how the graph will look like for the half wave rectifier? Correct?
Yes.
So what
Yes,
we are
sir.
doing is we are preventing the reversal of current in the circuit. So R will not have the current in the reverse direction. It will always have the current only in the forward direction. Understood? And the output is called, can we call it DC? It is like, yeah, it is fluctuating DC. It is not exactly DC. So we call this as a ripple. So what we have is a ripple. DC with ripples, DC with AC behavior. You can say it is a AC like DC, isn't it? The only difference is the other half we are not allowing, because if it is there, it means it is also AC. So this is your half wave rectifier. What they will, the first question they will ask is, what is the ripple frequency? There is something called ripple frequency. Ripple frequency of output waveform. So the answer will be same as the frequency of input, right? Because
Yes,
this
sir.
plus appears in the same fashion as this plus and this plus. So the ripple frequency remains same for input wave and output signal. You can say input signal and output signal will have same frequency. So we can write here note input and output will have same frequency in half wave rectifier. So these are some small fact which you should remember. That's it. I hope this is clear.
Yes, sir.
Yes.
Now there's something called efficiency of a half wave rectifier. So there are two things which we need to learn. Efficiency, they will not ask me, still we should know. Efficiency of half wave rectifier. So we can convert this entire complex device as a two-terminal device. So I can say there is an input. You can do like this. And there is a output. And this is the black box model, which means you don't know what is inside. So you have only access to the input and output. So if I assume the V input equals to V naught sine omega t, and this is the output. So this equation remains same, right? But it is only existing for the half interval. So V output is also the same formula, right?
Yeah.
Okay. So we may write like this, but the thing is we don't know what exactly it is. So you can, because there may be some resistance, the IR is there. So let's say if I assume the output current relation like this, if I plot the output current, so output is what? A DC current or AC current? So output is
Not
like a DC. Output is not AC, right? Output is like DC.
But not completely DC, no, like
Yeah, it is like
1 and 0. Instead of -1, it is 0.
Yes, it is unidirectional. Okay, so now tell me what is the average value? So for DC we find the average, for AC we find the RMS. There is a difference. So imagine this is given by a formula I equals to I max sine omega t. So what will be the value of I average from 0 to how much is this? pi by omega, correct? Half of the time period. So how to find the average value? Tell me, guys. Average.
Sir, we integrate I naught sine omega t and divide the value by pi by omega.
Correct, correct. So do it.
Yes, sir.
So it is I, you can say I dt upon dt. That's it. That's the definition. You can say 0 to t by 2. So how much is coming? Tell me after doing the integration. The output should be called close to AC or close to DC. That's the question. Tell me. The output is close to what? AC or DC? No idea.
Sir, I don't understand the question, sir.
Whatever output we are getting here, is it behaving as AC or DC? Okay, is
Sir,
it
from zero,
it is bidirectional or unidirectional? That's the simple question. Is it bidirectional or unidirectional?
sir, it's unidirectional.
So anything which is unidirectional is close to DC.
DC.
AC means bidirectional. Something which is bidirectional we call AC. Always remember this. Understood?
Yes.
And rule is for unidirectional voltage or current, we calculate average value. Why we do so? Because we know that the average cannot be 0, right? But
Yes,
for
Yes, sir.
bidirectional, the average is 0. So that's why what is preferable there? RMS value. And RMS gives the DC equivalent, right? So in AC, the DC equivalent is RMS. Okay.
Yeah.
All right.
So I average in this case is 2 by pi.
2 by pi.
Yeah.
It should come in terms of I naught, no?
Ah, sorry, I not 2 by pi.
I naught 2 by pi, no?
Let me
Sir,
check.
4 I naught by t.
How
So
much?
So 4 I naught by t.
By T. No,
T is
why
pi
T?
by omega.
It will only come in terms of I, not.
Just 1 second.
Sir, I'm getting 2 I naught omega by pi.
Let me do this.
Sir, and I also have a doubt based on a definition.
Yeah, just a minute.
Okay, sir.
So the I naught we can add a sine theta. Okay, we can get it easy like this upon 0 to pi. This is easy for you to indicate. And sin theta is minus cos theta, which is 2. We are finding the average from 0 to 2 pi only. This is entire value.
So 4 I
Yeah.
naught.
The
I actually found
average,
from
yeah,
0 to
yeah,
pi. Right?
yeah. The average will go from 0 to the whole value, right? 2 pi.
Yeah.
So this is the area we are finding, and of course there is nothing, no graph is existing there. So the numerator will be pi by omega, but this will be the whole interval we have to take.
Yeah.
Because we are trying to find the average for the entire cycle. So, but in the entire cycle, only half is existing, half is missing, right?
Yes, sir.
So the numerator will be, of course, pi by omega, because after that there is no graph. I mean, graph is 0, but the denominator will be 0 to entire interval. That's why the answer is okay. I mean, what you're getting is also correct. Just make a small change. The answer will become how much? I naught by pi, right?
Yeah.
Yeah. Now tell me, Hasika, you had some doubt.
Sir, is there any condition upon the magnitude for DC current?
DC current. No, DC means only if a DC is constant, then we simply call DC. If DC is variable, we have to take the average of that value. Okay, and that is we do it for the calculation of power and all. Okay, so if something is variable, we can take average, and we can take that average as a constant and deal with the question.
Okay,
You
sir.
take average and treat average as the constant value. That's it. Understood?
Okay, sir.
That
Yes,
is the
sir.
whole idea actually.
Okay, sir.
It is clear?
Yes, sir.
Okay. All right. So the output we are getting across the something called load resistance. So there is a load resistance across which you take the output, and whatever current flows here, the IRL becomes the output. Okay. Okay. So now we'll talk about the efficiency. Okay, now we got the DC current. What is the IRMS? What will be the IRMS value here? IRMS for output current. No, RMS for not output, or it is for the input only. IRMS. So if we have the I equals to I naught sine omega t, but the graph is only for the half cycle. And instead of DC value, if you want to find the RMS value, what we can get? RMS value. Just a minute. Yeah, fine. So find the RMS for the half cycle. Like, of course, you will take this from here to here, but the graph will be only from
0 to 500.
yeah 0 to t/2. So IRMS by definition is what? I square dt upon dt.
Shoot.
But what we know here that I square dt will only exist for and then from ty2 to t it is 0, isn't it? Because there is no
Yes.
graph. But this is t always. So how much is coming after this?
Sir, I naught by 2.
Very good. So for half wave rectifier, it is I naught by 2, the RMS. And the average is how much? I naught by 5. Understood. This is how we think of RMS and average. And the question is why we are taking this RMS and average, because we have to write two things. Efficiency, we have to write always in terms of power. So efficiency of a device is written as output power upon input power into. So efficiency of half wave rectifier, we have to write like this. And we know that in a forward bias case, because we are trying to find the current through a resistor in the forward bias case, think this carefully. So we do have some input here. We can think as input here. This is load. So in the forward bias case, what happens? This will act as a. So in general, it will have some resistance called the forward bias resistance. So what is the output value? Tell me. So can we write output equals to VI by RA plus RL into
Yeah.
RL? The simple normal circuit equation, right? So the same thing we can write in terms of maximum value or minimum value. Okay. It is clear what I'm writing here?
Yes.
Yes.
So this is how the actual circuit we can think of when we solve the question. So question is how to write the efficiency. So the question is how to write the power first. So to write the output power, see, we have the input signal is sinusoidal. And to write the power, what we need
Sir,
is, yeah.
sir, for the last 2 minutes, my internet was not very stable. Can you just explain after you had written the formula, sir?
Yes, so after the formula, you can think of a diode circuit as something like this. With a diode in the forward bias condition will conduct the current. So we are not getting current always, right? Only when it is positive cycle, we do have a current.
Yes, sir.
In forward bias condition, sometimes we replace the diode with some forward resistance which it offers. In ideal case, we ignore it, but we should take in general case. Okay.
Okay, sir.
So whatever energy I am giving, think about this. I am the source. Whatever energy I am giving, is it energy only consumed by the load or by the forward bias diode also?
Sir, by that also.
Are you guys getting my idea what I'm saying? See, I am the producer of energy. Am I the only consumer? Am I
No.
getting all the energy from here? Load? Tell
No.
me. So some energy is consumed here, some is consumed here, isn't it?
Yes, sir.
Okay. So what is the total power given to the system? So think about it. What is the power? What is the power given to the system? What is the input power? So can we say this is the IRMS, because input is RMS, we can think of. And some is consumed by the forward resistance of the diode and some with the load. Correct?
Yes, sir.
Yes.
But output is only through the load, right? So what exactly we are getting as the output? Because see, a device internally is also consuming some power. So my output power is not 100%. How much we are getting as output power? I average square RL. Now you may be wondering, sir, why I have taken average in the output and RMS in the input? Can someone guess this answer? Why I'm taking this?
It gets that rectified and converted to DC.
See, input is always AC. Only output is DC, no?
Yeah.
Input is AC only, output is DC, and input is AC means, although I'm getting only half cycle answer, but whatever I'm getting is input is AC value. So the effective value of AC we write in terms of RMS, and effective value of DC we write in terms of average. If something is only positive, we take the average to make it constant. But if something is positive and negative, we take the RMS for the effective value. So this is like a convention that is being followed by the most of the you can see calculation method. So how to write the efficiency of half wave rectifier? Output upon input into 100, right? So output is I average whole square into load resistance, and input we can write as I RMS whole square into the RA plus RA into 100. So percentage efficiency of half wave rectifier turns out to be how much? What is I average, by the way? Tell me, guys. What is I average value? I think we got the answer. No?
Right.
I not by 5. What is I average value? I not by 2. RL by. So this turns out to be 4 by pi square. 4 by pi square RL upon. Okay, what is 4 by pi square into 100? What is 400 by pi square? Anyone knows? Which is 40.6 into RL by. So this is the value which you can mug up. Yeah. So for max, what is the maximum efficiency possible? For maximum efficiency,
RF equal to 0.
correct. So maximum is possible when we have a very nice diode with no forward resistance. So we make RF equals to 0, so we get the answer as the eta max we get always 40.6%. So you can't get more than 40.6% efficiency in case of half wave rectifier. I hope this is kind of clear. Is it clear?
Yes.
Yes, sir.
Okay. Next. So we do have something called full wave rectifier. Full wave rectifier. For full wave rectifier, we have two methods to create. The first is called center tap method. And second is called the bridge rectifier. So I will draw both of them one by one. Again, draw the circuit with a transformer. This is a transformer. Coupled with the secondary coil. And now connect with two diodes, D1 and D2. Okay. And what we do, because it's called center tap method, so we take the center of the coil and we ground it. So this is like a tapping process. We ground the center. And then there are various ways to draw the diagram. I mean, you can draw the way you want. You can draw like this also. This is also a nice way of drawing. In various books, you will have a different way of drawing. They can draw it. Either you can draw like this, or if you don't want this way of drawing, which is not nice in appearance, you can draw from here separately. Draw, make it RL, and again make it ground. So either you can take this point and connect it here. It's the same thing, isn't it? Both are same.
Yes.
If I pick from here and if I connect here, it's the same thing. No? Anyway, I have to ground the other end. So you can do either this way or that way. Choice is yours. So which way is, I mean, preferable? This way or the other way? This is okay. Again, we have made the center geo so that we can have the one of the diode that is forward, other is reverse, because that is a reference line. So imagine if this is plus, this is minus. So which diode is forward bias? Yeah, tell me. The diode which
Sir,
is forward bias is
D1,
yeah.
sir.
So when D1 is AB, then can we say D2 is AB, RB? So the moment you call D1 is AB, the forward bias, D2 is bound to be reverse bias? Yes or no? Tell me.
Yes, sir.
Everyone.
Yes.
Yeah.
Hello.
Yes, sir.
So current will flow in this fashion. You can draw like this. Now when D1 is reverse bias and D2, okay, so when then D2 is forward bias. Now current will flow like this. So direction of current flow in both cases through the RL is same. So are we getting the unidirectional current in the RL? Yes or no?
Yes.
So we are getting anyway. So if you have a graph, you can plot it quickly. So if you have the input graph like a sine function, the output graph will be So what is the time after which the output is repeating itself?
T by 2.
Same as before or half the time as before?
T by 2. Half is before.
So what is the frequency of the output frequency or the ripple frequency?
Double
So ripple frequency is double the
initial.
input
Input
signal.
signal.
Input.
Double the input waveform voltage or whatever, right?
Yes, sir.
Understood?
Yeah.
So here the frequency becomes double. So this is the first question they will ask you. That in a full wave rectifier, the ripple frequency, or you can say the frequency of the output waveform will be same as input, double as input, half that, something like this. So I hope you know this answer. It's double the input frequency because the repetition is only half, you know. So the graph is
Yes.
repeating after every t by 2. So the time has become halved. So frequency has become doubled. Any doubt in this? Tell me,
No.
guys.
No, sir.
No, sir.
And direction is always balanced. So again, two things you need to find. The first is average and RMS. So because it's repeating after t by 2, so we have to find the answer only for t by 2 because average from here to here is same as average from here to here. Is same as average from here to here, yes or no?
Yes, sir.
Because area will become 3 times. If you make the time double, area is also double. So it really doesn't matter whether you find the average from 0 to t by 2 or t or 3t by 2 and so on.
Yes, sir.
So the I average, if you find here, you get the answer is 2I naught by pi. I RMS will be how much? If you remember the answer?
I have it.
Not by
Root.
2.
It will become root 2. Okay.
Yeah.
So this is the answer which is typical, which you know, but in a half wave rectifier, the answers are slightly different. You have to be very carefully while deriving the answer. Okay. And again, it's the same thing. Once you have this diagram, you can find the efficiency in a similar fashion without any ambiguity. So what is the frequency, sorry, efficiency of full wave rectifier? So can we say the output power upon input into 100? The graph remains same. It is again the same diode, same load. And input, output. But this will also offer you RF, right? So the power is consumed by the RF and RL both. So you can write as I average square into RF plus into RL, correct? This is the output. Because we get the output only from the load resistance. But input means the total consumption of energy. So energy is consumed by the RF
Both
as well as
are-
RL, correct?
Yes, sir.
Into 100. So what is the answer now? Tell me, guys. Average, we know it's 4I naught square by pi square. I RMS is this by 2. So it's a double answer, right? Full wave will have double answer. So what is the answer coming here? 8 by pi square. So it is, I think, how much? 81.2. Yeah. 81. So what is the maximum efficiency of full wave rectifier?
81.2%.
81.2.
When RF is 0, right? It is clear?
Yes, sir.
The next part is called the bridge rectifier. How we design it? It's very simple in design. Bridge rectifier. So in bridge rectifier, we take 4 diodes. We find the output from across this, and then we have the input source attached here. Okay. So let's begin. For positive half cycle. So positive means this is high, this is low. Okay. So for the positive half cycle, which diodes are forward biased?
D2 and D4, sir.
Correct. So when plus is here, then D2 is forward bias. And when minus is here, so then D4 is forward bias. Yes or no? Tell me, guys.
Yes, sir.
Hello,
Yes,
hello,
sir.
hello.
Yeah.
And therefore, if
Yes,
you look
sir.
at the path of current, current will go like this, this. Oh, back to the power. So the current through the load will flow from where to where? Right to left, to left to right.
Right to left, sir.
Right to left. Everyone is getting the answer. So for this case, the current direction is like this.
Yes, sir.
So for positive half cycle, D2 and D4 are AB. 1 and 3 are RB. So if I name it AB, or maybe I can name it somewhere here. A, B, C. So current will flow from D to D. Yes or no? Tell me, guys.
Yeah.
Yes.
So for negative half cycle, for negative half cycle, what we can say? So negative means what? This is minus, this is plus. So D3 is forward bias
Yes.
and D1. Do you guys realizing what I'm saying, or you are finding it difficult? Tell me. You're realizing this?
Understood, sir. Yes.
Yes, sir.
Okay. So D1, D3 are forward bias. So D2, D4 will be.
Reverse.
So what will be the flow of current direction of flow of current?
D to B.
So now because one is forward bias, so current will go 1 and 3 are forward biased. So 3 will set 3 will enter here, will go here, will come back here. So you can see the path. The flow is still B to D, right?
Oh, yeah, it's B to D. Yes.
So current will again flow from. So we make sure the direction of flow is same. That's why it's called unidirectional. Okay.
Yes, sir.
Yes, tell me.
So could you please show the current path again? I could not get it.
You have to start from the bottom.
Hmm.
So D3 is forward bias, so you can go like this.
Hmm.
Then you can't go through D2, right?
Yes.
You will make a turn.
Yeah.
Then D1.
Hmm.
And come back.
Okay.
Path is clear?
Yes.
Tell me guys, is this clear? The path is clear?
Yes, sir.
Yes, sir.
So the direction of current is maintained, no?
Yeah.
So the direction in which current is flowing through the load through which you're taking the output, that is same. It means it's a DC. DC means like a one direction, unidirectional current, right?
Yeah.
Okay. So tell me if you have any doubt in this.
Sir.
Yeah.
Sir, when the current reaches point A,
Hmm.
then D2 is forward bias now. So it can flow through that point also.
No, current, how current is reaching there? Current means like we need potential difference, right? So current is flowing, it means there is a drop. There is a drop of voltage, right?
Got it.
Yeah. So now comes the filter circuit, right? So it's just a circuit which you need to know, because sometimes they will ask you, do you understand this? Yes, no, or whatever. So okay, there's one more thing left, I think. For every diode, we have something called the input and output characteristic. So in case of diode, which one is dependent quantity, voltage or current?
Current.
So as you will change the biasing voltage, the current will change, right?
Yes, sir.
Yes.
So we always draw the current as output on the y-axis and voltage on the x-axis. Okay.
Yeah.
A positive voltage means forward bias. Some rules you should know. So for PN junction, positive voltage means and negative voltage means so any graph on the right of the origin will be graph under which biasing? Graph under forward biasing.
Yeah.
Understood?
Okay.
And on the left will be reverse biasing.
Yeah.
Now what you need to remember that in case of forward biasing, the current which will be dominating in a circuit is called the current due to majority charge carrier. But in the reverse biasing, what happens? The majority stops, but current do not stop. Majority stops. So who will get the access? Minority, isn't it?
Yeah.
In the reverse bias, what will happen? Tell me, guys. In the reverse bias, the majority cannot flow across the depletion region. Yes or no?
Yes.
Yes.
Okay, I also need to discuss about the biasing and depletion region effect. Okay, come to this. Anyway, so the graph, okay, if you remember that there was something called barrier potential, right? If you remember the barrier potential,
Yeah.
Yes.
even though a diode is forward biased, will it conduct current?
Not until it overcomes like the potential. variable.
Yeah, so unless you are not crossing the barrier, so V must be more than barrier, then only conduction will start. Yes or no?
Yes.
That is why if you plot the graph, till the barrier, can we expect any current? No, it is almost flat, 0, 0, 0, 0. And near the barrier, you will start seeing some current. And then the moment you cross the barrier, it goes to infinity. When, of course, not this much slant, it may be more slant. Infinity doesn't mean infinite, it means the current will be in the milliampere range. That's it. Sometime in the ampere range, the diode will burn out. Why? Because there is a rating of a diode. So if you remember, what is the power consumed by the diode? Power consumed by the diode. How much? If you remember, in a rectifier, it was IDC square into RF. Do you realize this? The DC current for a rectifier. Okay, I should have talked about this for rectifier. Can we say this? How much power diode is consuming itself? See, in the output power, so in the
Yeah, got it.
input power, we have two energy. Okay. No, I should have written IR, my bad. In the input power, we have two consumer, RF and RL. Understood?
Yeah.
So how much is consumed by the this diode itself? I should change this to RMS. Just a minute. So for rectifier, if you remember, diode is also a consumer, no?
Yes.
And every diode will come with the power rating also. Okay? Power rating means what? If you dissipate more than certain amount of energy, the diode will burn out or will get damaged. So this is like a having a fixed specification. A manufacturer will give you the rating also. See, this the diode will work only for this milliwatt. Now, what does it mean? A milliwatt will make sure that the IRMS square RF cannot exceed this value. So there's something called power rating of a diode. So when you buy a diode, it comes with power rating also. So commercially, they mention everything. There's a whole lot of, there's something called a specification sheet, which they provide when you buy this thing, which you can read and understand that what is the operating voltage, current. So too much current is also dangerous. Too much power is also dangerous. So we have to take care of each and every condition or constraint which they provide. Understood what I'm saying? So a diode will also consume, and if it is too much, it will burn out. So anyway, our graph is saying infinity. Infinity means it is close to the value which is equivalent of the power rating suggested. Okay.
Yeah.
Yes, sir.
Now you can see the graph is slightly curved near the bending, this part, but it is mostly straight line, right? Mostly straight line, because in the majority flow of current, when you have a large current flowing, in that case, the diode acts as close to conductor. So it will behavior will be similar to conductor. Once the current magnitude is reaching in the milliampere range, large value, so it is having almost straight line behavior. The curvature is not so significant, but there is a transition phase. So near the barrier potential, things are very non-linear, isn't it? It is quite non-linear, and that is why the resistance of a diode is not same all the time. You can see clearly, is the resistance same all the time?
No,
So
sir.
in the very beginning, the resistance is almost infinite. Correct?
Yes, sir.
and then resistance will start decreasing, and when it is very slant, then it will have lesser resistance. So we define something called dynamic resistance of a diode. So dynamic resistance is always defined in terms of the slope of the graph. For the flat part, you can take, so every point will have different. So we take for the flat part, so you can draw a line. This is V, this is V plus delta V. This is I. This is how much? I plus. So you can see there is a slope here. Delta I, this is. So dynamic resistance we can write as RD. And dynamic resistance, why I'm saying dynamic? Because it is not same all the time, right? It is changing dynamically. And it is changing as the bias voltage is changing. It is changing as the current is changing. So dynamically, what is the value? Delta V by delta I. Is this clear?
Yes.
Yes, sir.
And see, this is the graph which is letting us know or saying that, okay, see, a diode will always have some forward bias resistance. So this will become later on RF. But this is not exactly RF, but it is the idea of RF. How exactly RF is calculated? So there is a different theory called the load line analysis, which we use to calculate the RF. So in the BTech second semester or first semester, you are going to study all this. Or those who have taken elective as electronics in high school, they might have studied. So these all are the experimental procedure. Also remember that when I draw the graph on the forward bias region, this is the AB region, the forward bias region. So the current will represent which current? Flow of minority or majority? So this
Majority.
always represents the majority charge carrier. Now, once we go to the reverse bias, what will happen? The majority will stop. But you are going to facilitate the minority, yes or no?
Yes.
Yes, sir.
And because you are facilitating the minority, so current will be available in the reverse direction. But minority, because of the name minority, you cannot get large values. So the current magnitude will drop to the microampere region. Okay. And this current in the reverse bias will, okay, I will zoom it because this is the microampere scale. So it will decrease and I mean, let me just change the color. So it will be like increase and will become almost constant. And when you make the reverse biasing too large, then there is something called the dielectric breakdown, or there is a zener effect, and current becomes again infinite. Okay, so you can draw something like this. This is called the knee voltage. VK. Nice. Knee voltage. It's like a knee in the shape, so it's called knee voltage. And we are also going to call this as the zener breakdown voltage. So as of now, because this is not a zener diode, so we use the word knee voltage. But once we have the zener diode, we are going to change that as a zener breakdown voltage, VZ. So we will change that answer for sure. Okay.
Yes, sir.
The graph is clear.
Yes, sir.
Yes. Sir.
See, these graphs are actually drawn almost touching the line. I mean, you can't draw anything like this. It's almost touching the line. But just for the sake of illustration, I have drawn with a gap. So this is a fraction of a microampere. So you can imagine that anyway, the minority charge carrier will be minority charge carrier. Okay. So this is called the reverse saturation. This is called a reverse saturation current. What do you call? Reverse saturation means it's constant. And the question is, if it is so small, then what is the benefit of studying this, the reverse biasing? How it is useful in our life? So when we design the optoelectronic device, there is a device called photodiode. Now, when light ray, the intensity of light when falls on the photodiode, it ejects the photoelectrons as per the photoelectric effect. But this ejected photoelectron will create a current in microampere range. Now imagine if a diode is forward bias, current is in milliampere. Is it possible to detect a change of microampere range in the milliampere scale?
No.
No, sir.
But imagine the diode is reverse bias and the current itself is in microampere, and then you add 10 microampere more. Can this be observed easily?
Yes.
Yeah, because that change will be significant. We can see it easily. So if we have, if you see that there's a match is abundant due to the poor lightning condition. So they use the same photodiode as a device. In the cricket ground, they see the intensity, and there is as per the protocol, there is a value which they have assigned. Once it crosses that value below certain threshold, they stop the match. They decide or declare that, okay, this light is not sufficient. If it is more than that, they can continue playing the match. I hope this is clear.
Yes.
So the idea of dynamic resistance is clear. What is dynamic resistance? A diode cannot have the static resistance. They always have a dynamic resistance. How you are going to understand? Okay, I have to calculate this in the examination. They will give you the V plus minus value. So you take the delta V, you take the delta I for the given V, and take the ratio, you get the dynamic resistance. I hope this is clear. Okay.
Yes.
So after this input and output characteristic or the IV graph, so always remember this is always the IV graph, also called the characteristic graph. So now comes the filter circuit. So what is filter circuit? The rectifier cannot give you a good value, a nice value. Rather, it will give you only the unidirectional sinusoidal wave, right? So the graph is still the sine curve, but it is unidirectional. So all the reverse direction we are eliminating. So if we have a rectifier circuit, so imagine if you have a half wave rectifier. And if you have the input signal, the output is going to be again what? Something like this, isn't it?
Yes,
But
sir.
this is not nice. This is not good, and we don't want something like this. So what we do is we connect a capacitor in parallel with the load resistance, and we are going to get the output from the load itself. And if I call this as the peak value V naught, so the potential across the capacitor, which we keep here as, because we have a diode here, which I haven't shown. So that diode will offer you, if it is a real diode, it will offer you some barrier potential light.
Yes.
So in a half wave rectifier, we had a diode with some barrier potential. So what we do is, we first of all keep the capacitor already charged, and the charging we keep as a V naught minus VB, because you cannot charge with V naught, right? So this is called the peak charging. This is called the peak charging. So I make sure that it is charged to the peak value, and V naught we keep as much bigger than the VB. So it is almost V naught, isn't it? Correct?
Yes.
So now what will happen is,
Yeah.
when the output wave will come here, okay. So there are two possibilities. If the output is less, the capacitor will discharge. And if output is more than this potential, then capacitor will charge. So it is like, if you have a capacitor which is already charged, think about it. And if the voltage you are applying, if the voltage is exceeding the VC, so imagine if the voltage is exceeding the VC, the capacitor will be in the charging state. Yes or no?
Yes, sir.
But below this, it will be. So the red is what?
Dis-
Discharging state of capacitor. So I can make a legend. This is legend. Red, blue. So red is the discharging. And blue is the charging state. Okay. And this is the incoming wave coming to the capacitor, right? So we are going to obtain the voltage from where? The RL. Okay, so imagine RC circuit. If you know RC circuit, so it is like RC circuit. RC circuit. And you're charging with a peak. So this is the rectified output. So this is the rectified output coming to this. And we keep the capacitor charged initially. So what happens if the applied voltage is more than the peak voltage of the capacitor? The capacitor undergoes the charging state, and then in the charging state, who will decide the current from the R? This or capacitor? The incoming signal will decide the current, or the capacitor will decide the current?
Incoming voltage.
Incoming.
Very good. During charging process, it means if the input signal voltage is in the blue region, then the voltage across R will be depending on the incoming signal. Okay. And this gap is not, we try to keep the gap very small so that it is close to the peak value. So it's a highly exaggerated graph. It is something like, so we have almost this region as a charging region, this region. That's it. Rest is discharging region. Technically, you have to think this way. So if you're really understanding it, it's really good. So in the first phase, in the charging phase, the current, so now because it's the charging, the current through the resistor or the load is due to which voltage? A voltage close to the peak value. So can we say current? So for charging state, listen carefully. For charging state, I through the load will be how much? Can we say it is close to close to what?
B naught by RL.
B naught by RL. Tell me guys if you can say or not.
Yes,
Now, what will happen for discharging state? If the applied voltage has gone down to the very low value, close to zero answer, then who will dominate?
capacitor.
And then capacitor will start the current flow. Understood? The capacitor
Yes.
will start the current flow. And then the voltage across RL will be depending on the capacitor voltage, which is anyway we know. So in the discharging state, the IL is again close to V naught by RL, isn't it? Again, I'm not saying equal. It is V naught minus VV, but it is roughly same, right? So what we are able to do is, we are able to maintain the potential across the RL with a small fluctuation. So how the graph will look like for the actual output now? So this is what you have to learn actually. Slightly difficult to understand, but just remember this fact. So if you plot the graph of the rectifier output, what is the rectifier output? It is actually like this, then nothing, then like this, then again nothing, then like this. But what is the filter output? Filter output is not that. Filter output is quite different. It is, see, as long as the capacitor is charging, the current in the RL will be above this threshold, right? Now here, this is the threshold of the capacitor. If you try to go below, then capacitor will decide the current flow. So it will, so now this is the discharging state, then capacitor will charge to the peak value. When capacitor will start discharging, listen carefully. The next cycle of the input wave will come from the rectifier output, which will again make the capacitor charge. And while discharging, it will again go back to the. But again, while it is discharging, when the capacitor is discharging through the RL, again the waveform will eventually reach. And we make sure that the input waveform is coming much before the voltage across capacitor drops to certain value. Are you getting a point? What is happening here?
Yes, sir.
So this graph is, now you can see this is at least better than before, right?
Yes,
So it is at least, let's say this is not exactly constant, but it is close to constant. So this difference of the constant, it is not constant, it is still changing. So this is called ripple. So we have the ripple output, which is a DC with some fluctuation, but it is not as fluctuating as it was before. The filtering process is making it more nicer, more flatter. So now imagine if the input signal is coming at a fast rate. It means if the discharging, if the time constant of the circuit, if the time constant of circuit is much bigger than what? Much bigger than the input frequency of signal, right? Then
Yes, sir.
capacitor will never, it means capacitor will never be allowed to discharge by large value. The discharging will take place for very short span of time. And before I discharge, I will get the next waveform, which will make me charging. Understood what I'm saying?
yes, sir.
So the condition, they will ask you the condition that the input frequency and RLC, what is the relation? So you can see the input frequency, the tau is much bigger than the frequency inverse of input signal. And this is also a condition in communication chapter. This is the same thing which is called condition for demodulation. Condition for demodulation. So the filter circuit, so tau of the filter circuit must be more than 1 by f. So this condition you can just keep in mind. And if you do it for the full wave rectifier, it is different answer. So you can say f input is how much? Much bigger than 1 by RC. Same thing, right?
Yes.
Okay. So, okay, anyway, rest you can read my notes. There's something is written there I can refer to. So now we can go to the next concept quickly. That's the last concept of diode, which large questions in JEE-Mains has been asking for the last few years. Zener diode. Of course, the name of the scientist is Zener, something Zener. I don't know exactly. Okay. Am I audible?
Yes, sir.
Hello.
Yes,
Yes.
please.
Okay, so
Yes.
a bad news, the entire thing I've written is now gone because of the internet disconnection.
Yeah. Oh,
So you have to watch the video. I mean, the video will be there. Don't worry, video will be there.
It's fine.
But the PDF has gone. So what you are supposed to do is from the video, write the PDF, write the notes, and then share among yourself.
Yes, sir.
yes, sir.
So who will take this honors of creating the PDF?
Sir, Parth.
Okay, Parth will do it then.
Yes, sir. I don't.
Sir, I've
Okay.
written like most of the notes today, so I can share.
Yeah, great. Only the last, okay, Zener. So I was about to save it, but that time only it's gone. Okay. Oh. It feels really bad when you lose. Zener diode. As a voltage regulator, okay. Okay, so I was talking about the effect of biasing on depletion region. Okay. So if you have a PN junction diode, we know that there is a default thickness of depletion region, right? There is always a default, isn't it?
Yes.
Yes.
And that is due to the diffusion process. If you remember, I have discussed this. So let's say if you do the forward biasing of the diode. So when you have the forward bias, what will happen? The positive charge will come to the P, right? So some holes will come. You can think there is a flow of holes here, and there is a flow of electrons here, isn't it? Hello, hello, hello.
Yes, sir.
Yes, sir.
So the depletion region, which was devoid or deprived of the charge carrier, the missing charge will be replenished, right? Isn't it? So these holes will replenish this empty charges, right? And the electron will replenish this. So as you replenish the layer, so now those layers which are replenished back with the charge, can we say that as depletion? The answer is no. Now they're part of the regular PN junction, right? They're not part of depletion region, isn't it? Are you getting what I'm saying? Hopefully not. Actually, imagine we have 1, 2, 3 layer. I'm just doing only one part. Minus. Okay. And what is we are providing from here? Holes, correct? And from here,
Electrons.
so this hole will come and occupy this and this will. So now this layer is now replenished with the charge. So this is not a depletion. Now the depletion is from here to here, right? Isn't it? Every layer where you give back the charge, it is not depletion region, no?
Yes, sir.
So the depletion, as a result of forward biasing, what happens? The depletion region will shrink or grow.
Shrink.
It will shrink. It will decrease. Yes or no?
Yes.
Yes, sir.
Tell me, guys, if it is making sense to you. Yes or no?
Yes, sir.
So as a result of forward biasing, the depletion region will become thinner. So the reverse will make it thicker, isn't it?
Yes, sir.
Yes.
You can just think about it. So I'll just mention this here quickly. In case of forward biasing, the thickness of depletion region will shrink, whereas in case of reverse biasing, the thickness of depletion region will increase. And this is the beauty of the depletion region. It can grow, it can shrink. And the growth and the shrink we can actually put to our advantage in various situations. So when we design a transistor, so you will study that this property of increasing the thickness can have benefit also. So we'll see what are the benefits. So when we design the transistor, very soon we are going to see the transistor also. Okay. So what is
Could you
zener?
explain the reverse bias case once again?
Same thing. I mean, reverse bias. What you're going to supply here? In the plus, plus, plus. Minus, minus, minus. And in the reverse biasing, you're actually giving holes to this part, right? and electrons to this part.
Yes.
So this electron will eat away one more extra layer. And the hole will eat away one more layer of here, isn't it?
Sir, but the depletion region grows because there is diffusion, right? And
No,
if there
diffusion
a
is done.
voltage-
No, diffusion is done. Diffusion, now
Okay.
we are pulling extra layer electrons and holes away.
Okay.
So battery is providing some electrons which is consuming those layers.
Okay.
So you eat away the free charge carrier from the location close to the depletion, and because you are eating away, so the region will grow.
Understood.
And these all growths are in the micrometer and less. So it is not a big growth that you can see. Oh my God, it's really thick. The entire chip is how thin? Have you seen the chip? Hopefully. So if you tear apart the SIM card, you can see the chip is in third layer. First you tear apart the SIM card, then you will get a plastic bag, then open the plastic bag, you will get some layer of plastic. Then from that layer, if you remove, you will get the chip. It's so thin. So it is like a tip of a ball pen. That thin chip is, running this entire communication network. Imagine how powerful the chip designing is. So these are like, the tiny layer you cannot think about. Is this clear? Okay.
Yes, sir.
What is zener diode? A zener diode is okay, it can be highly doped diode or it can be moderately doped diode, but it is slightly doped above the average. So zener diodes are made by the p-n junction diode with slightly high doping concentration. So zener diode, and they are just diodes, nothing more. Only in the reverse bias they behave something interestingly. So we'll try to discover what is the reverse bias behavior of diode, which we call zener diode. So in a zener diode, what happens? It acts as a voltage regulator only in the reverse bias, but in the forward bias, it is as good as normal diode. Okay, so what we can write? Zener diode is zener diode acts as general diode in the forward biased condition, but in the reverse bias condition, it acts differently. Okay. So when reverse voltage exceeds the threshold voltage called zener breakdown voltage, then it maintains a constant potential across its terminal and hence act as voltage regulator. So in electronic circuit, sometimes we want to prevent, our sensitive device from a sudden you can say rush of current or sudden increase of voltage. So any part of the electronic device which is very sensitive, depending on how sensitive it is, we design a zener diode. So we design it actually. So we choose certain specification so that it is not going to burn out. Okay. So we'll first try to understand what is happening in the reverse biasing condition. So if you remember the reverse biasing, and if you put out the IV characteristic of a PN junction, so you have seen that in the reverse bias condition, the current is almost constant. And not just constant, it's almost zero also. And just after some negative value, it becomes almost, you can see. So if you look at the graph carefully, what is constant here? What is constant here?
Voltage.
Voltage is constant here. And now current is the, see, we have no control over the current. So current goes to any value. In fact, current becomes so large that it can go up to 1,000 times, that is in the milliampere range. So this reverse current can go up to milliampere. So we are drawing as an infinitely long line. It's like a infinite line. The reason is if something from milli goes to, sorry, something from micro goes to milliampere, the growth is how many times? 1,000 times, right? So a reverse current going from micro to milli is called infinite. And you can clearly see what is the slope here. Slope is almost 90.
Yes, sir.
So resistance is almost zero. So the diode will behave as a short circuit without any resistance. But it is short circuit with constant voltage. So you can say voltage is constant. So the voltage across the diode will never change. And therefore, if you have something in parallel with the diode, it will be regulated by this voltage. But this voltage is only attained if you cross this threshold value. Okay. So in the zener diode, there are two mechanisms by which this breakdown takes place. So I have talked about the zener breakdown. I have talked about the breakdown voltage. Okay. So there are two types of breakdown mechanism. Okay. But the thing is, because of some historical reason, these two mechanisms now we called in both cases we only use the term zener diode, but we have two separate mechanism. One is called the mechanism. So mechanism for sudden surge of current in the zener diode. Okay. In reverse bias condition. In reverse biased. So we have seen one thing, if you remember, as you increase the reverse bias, the depletion region will grow or decrease. What will happen? Tell me. With reverse biasing, the depletion region will grow,
Yes.
isn't it? That is
It
for
will
Yes,
sure.
sir.
grow.
So let me discuss the zener first. Zener breakdown. Imagine if you have a semiconductor PN junction diode which is highly doped. So a highly doped semiconductor PN junction diode will have very thin layer of the depletion, as we have discussed.
Yes.
How many of you remember this? Recall this? That highly doped semiconductor will have very thin depletion region.
Yes.
So
Yes.
one side it is highly doped, and then you have very thin region of the depletion. So the field becomes very large, and this field can sometimes can be strong enough to tear apart the entire bond present in the depletion region. You break the bond, covalent bond. Okay. Because these are from the group 4A, no? So in group 4A, you can break the bond because you have a large number of catenation, right?
Yes.
And once you break the bond, see, just like carbon, silicon also exhibit the catenation property, isn't it?
Yes.
So they have a lattice structure. They don't are, I mean, they are not like other elements. They are like lattice with bond everywhere. So once you have once you have the very strong field and the field is existing in the depletion region, that field will be powerful enough to break the bond and it will create what it will create? Electron hole pair. Understood? So what is happening here? We have P type, we have N type. This is the depletion region. And the field is what? Field was left, right? I think if you remember. And if you make the reverse biasing, so it will even grow, no? It was small, now it will become bigger, right?
Yes.
And the field is powerful enough to break the bond. So once you create the whole electron pair, how it will run away? So hole will go this side, and electron. So E will go to the N side, and hole will go to the which side?
P side.
Okay. And if it is happening, then in the circuit there will be current. Which current? What is the direction of current? Like this.
Yeah, in the direction of applied voltage.
Yeah. So this is the reverse saturation current because current should generally go from P to N, but it is going from N to
And
P. Okay. So it means the current should go this way. This is the expectation. How it is going? This way. Inside the P junction. So this way, therefore, what is happening? The breaking of bond will create a large number of electron hole pair, and that large number will run across the depletion region and hence will create a large saturation current. You can see IA has gone really up. You can see that graph, isn't it? Hello, 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 hello.
yes.
So this graph has gone suddenly up. No? The current has gone up. So this sudden surge of current due to the breaking of the bond in the depletion region and hence creating the large electron hole pair, this kind of breakdown is called what we call zener breakdown. Now the question is, if there is a sudden surge, what are the risks involved? So see, a diode will have in a reverse case a large resistance. Understood? So what is the resistance of a diode? So resistance of a diode in the reverse bias is much bigger than a resistance of the diode in the forward bias. Resistance of diode. So technically, the reverse bias resistance is in the mega ohm, much more than kilo ohm at least. In the forward bias, it is in ohms. Understood? So a sudden surge of current will dissipate the heat a lot, yes or no? And that could be dangerous. That could be dangerous. Potentially, that heat can melt the entire diode itself. It can burn the diode. Some fume will come. So when we design the diode for the zener breakdown action. So we make the doping high enough to reduce the resistance. So even the reverse bias condition, we try to keep the resistance to a certain, slightly low value as compared to the regular diodes. And we know that you can reduce the resistance by increasing the connectivity, isn't it? And to increase the connectivity, you can increase the charge carrier concentration. Yes or no?
Yes, sir.
Yes, sir.
That's from current chapter only. So as you have more connectivity, it means we have large concentration, isn't it? And therefore, even with the surge of reverse current, the resistance is not good enough or not large enough to dissipate the heat, which can damage. So the power rating of the zener diode is generally very high. It can tolerate large dissipation without hampering the functioning. That is the beauty of zener diode. It can actually dissipate constantly some large value of heat, and yeah, large means milliwatt, don't worry. It is never watt. Everything is in the world of milli micro. Okay? So milliwatt is large. Yeah, that's correct. So this is how it is designed actually. So in the zener breakdown, things are very simple. What happens? You bring a highly doped semiconductor with very thin layer of depletion, very strong electric field, and the field will break down the bond, will create the electron hole pair, and that will create the sudden surge of current. But the designing is done in such a way that it is going to maintain the voltage in that surge condition. So current can have any value, but voltage will remain constant. Understood? Hello, 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 hello.
Yes, sir.
In examination, they will give you the VZ, that what is the breakdown voltage. So we'll come to that. The next part. The next part is called the avalanche or avalanche, whatever how you ever say. Avalanche breakdown. Avalanche. So generally, in the hilly areas, you must have heard about the avalanche. Okay. So avalanche means one after the other, right? It's like a domino effect. Something falls and that makes other thing also fall together, right?
Yeah.
So the question is when this avalanche will happen or will occur. The answer is very simple. If the doping is not enough, if the doping is not enough, what will happen then? The depletion will be thicker, right? So if the doping
Yes.
is not very large, then the depletion region will be thicker than before. Correct? Hello, hello, hello.
Yes, sir.
And if the depletion is thicker, so what will happen? The electron, although you can say charge carrier, will accelerate through it. So they will not have, see, the field is not powerful enough to break the bond, but at least the charge carrier can accelerate. So you know that the minority charge carrier will accelerate through it. And therefore, while leaving the depletion region, they will have sufficient kinetic energy. If this kinetic energy will exceed the bond energy, it will break the bond. And once it will break the bond, it will create some new electron hole pair. And this is like a chain reaction. So this new pair and the old pair will hit the another number of bonds, will break it. And there is like a chain reaction will continue. And the current will have a surge. So here the mechanism is different. Here the mechanism is collision process. Understood? So here there is a process of collision, just like the nuclear fission reaction. If you remember the nuclear fission, in which the nuclei breaks and releases neutron, the neutron will bombard the next nuclei, 3 nuclei, and 3 will produce the 9 neutrons, 9 will hit the, so there's a chain reaction. Similarly, in the avalanche breakdown, the accelerating charge particle will hit the bond, will break the bond, will create new charge particle, which will again accelerate further, will hit it, and this process will continue, and there is a chain reaction. And because of this chain reaction, the current will simply surge. So technically, this should have been called avalanche diode. Because again, I said it because of the historical purpose, the zener and avalanche both are called zener diode. But there is a difference. Avalanche means the release of new electron hole pair through successive collision process. And in a zener means what happens in zener diode? The field is powerful enough to break down or tear apart the bond itself. Hello. Is this clear, guys?
Yes, sir.
Yes, sir.
So theory I have written in the notes, you can read from there. But the explanation part is clear. What happens in the two process? So the first question, theoretically, what you should know? Zener requires high concentration, high doping. So I can say doping in a zener breakdown mechanism is much more than doping in the avalanche breakdown mechanism, right? So zener means field emission process. Avalanche is called collision process. So what is field emission? You apply the powerful field to break the electron hole pair. So here field is strong electric field in depletion breaks the bond and releases electron hole pair. Collision process breaks bond and the chain reaction creates large number of EH pair, hence IS increases significantly. I hope this is clear.
Yes,
Okay.
sir.
The next part is called. Can I take some more time?
Yes, sir.
Before you
Yes,
sleep?
sir.
Anyway, so quickly I can go to the next part called the representation. Now see, irrespective of the mechanism, what you need to remember is representation. Representation of zener. It's a very simple. So how we represent diode? A triangle. And for zener, write Z. That's it. And it will always come with a rating VZ. Okay. It means if the reverse voltage will exceed this value, then only it will act as a regulator. Otherwise, it will act as open circuit. So how to understand? Okay. Imagine this is at low potential and this is at high potential. This is the biasing. So how many cases are there? Case one. If the voltage across this is, first of all, this is reverse bias or forward bias? What is this? Which is the biasing type? Yeah, tell me, guys.
The reverse.
Reverse.
Yeah, it is reverse bias. Because this is the high, this is the plus, and this is minus. So minus is with plus, plus is with minus means zero low potential. So this is the reverse bias. So you have to check two things. Assuming it is reverse bias, we need to check if V is less than Vz. If V is less than Vz, it means on the graph, where are you? You are before the knee.
Yes.
So you are somewhere here, right? So will it act as a regulator? The answer is no. Not act as a regulator. So what to do with the diode? What we can do here? So the diode will be
Open
acting as
circuit.
open circuit. Very good. That's it. It will act as open circuit. Nothing will happen. So no current will flow because current is almost zero. So no current will flow and will behave as open circuit. Case 2. If V is more than equals to zener diode, so when you solve numerical, what will happen? It will act as
Regulator.
regulator. It will act as voltage source. So it will maintain the voltage. Exactly how much?
VZ.
Across the terminal, the voltage will be Vz. So whatever you connect here, so current through the load in that case will be how much? Vz by RL. Understood? Because the voltage across RL is maintained equals to Vz, isn't it? Hello, hello, hello.
Yes, sir.
Okay, clear?
Yes, sir.
So V will not matter. What will matter is Vz. Okay, and if a zener diode, now this is done. And the last concept of zener is if the zener which biasing is this? It is forward biasing, isn't it?
Yes.
Yes, sir.
And because zener is having highly doped semiconductor, so the barrier potential is very small. Tends to, you can think is zero only if it is not given, and therefore it will act as short circuit. Understood? So in the forward bias, it will act as normal regulator. Normal, diode, just like what you do with other diodes. Only in the reverse, it will have a different behavior. So if it is reverse, but not sufficiently reverse, open circuit. The reverse and sufficiently reverse, if it is exceeding the breakdown value, it is a regulator and it will regulate things like this. So we'll solve one question to understand how to solve question. Oh, that's like a rhyme. Okay. And then we can start solving the JEE-Mains question because there is a large number of questions. You can do any circuit with a zener diode. Okay. Or do a load parallel to this. And then we have the VI. This is VZ. So let's say this is 2VZ. Just for the solution. Okay. How we solve actually? So when the diode will be reverse bias for the positive cycle or a negative cycle? Tell me, guys. When the diode is going to be reverse bias, which case?
Positive.
Sir, for the positive.
Positive.
For positive, right? Positive cycle for sure, right? And that is logical enough. Because when it is positive, imagine there is no current elsewhere in the circuit. You don't think of current. So for positive half cycle, for positive half cycle, the diode will be in reverse bias. Reverse bias condition. Well, that's how it goes. Now, there is no guarantee that it is more than Vz. So we'll take the case one. So imagine if the V is less than Vz with positive half cycle. You know it's positive half cycle, but you also know that it is less than Vz. How the circuit we can redraw? Tell me. So we can draw this as a battery of value V, whatever it is, I don't know. The R is R. But this is open circuit, no?
Yeah, we can remove that branch.
So you just remove the branch. So what you are left with? RL. So the output will be how much? It is very simple. You know how to solve circuit.
Yes, sir. VI by R plus RL into RL.
Any doubt in this?
No, sir.
So this is how we solve. See, this is the assumption you have to anyway make. And you got this answer. Now check. Check. What do you need to check? Check whether this V out is more than Vz or V out is less than Vz. See, you assume that it is less than Vz. What do you assume? You assume that this is the entire zener diode is not part of circuit. You simply removed it. That is how we proceed. You simply remove it. Don't do any calculation. You remove it and find the voltage across RL, because we know RL is parallel to the Vz. So whatever voltage you will get across RL, the same is across Vz. So now if you check whether the answer you are getting V out is more than Vz or less than Vz. Okay, you can check these two things. If it is less than Vz, this is the answer. What you got? It means you first make assumption that assume that diode is not working. It is open circuit. And you got an answer. And then you realize that the answer given, the V out which you calculated, is actually less than Vz. The reality and the assumption coincides. So the answer which you got, V output, is same answer, isn't it? Right, guys? Hello.
Yes, sir.
So in this case, if V out is still less than Vz, if this condition is still satisfied, so we started with the assumption and then we saw actually it is satisfied. Then can I say the current through the load will be VI by R plus RL?
Yes.
Done. But if the output which you calculated with the confidence that okay, it is an open circuit, turns out to be Vz, oh my god, then the scenario will change. Yeah, it will act as a regulator, isn't it?
Yes, sir.
So what will be the current through RL now? The IL becomes now VZ by RL. Yes or no? Hello, hello, hello. Understood? Because now this is parallel, these two are in parallel. So voltage across
Yeah.
RL will be going to be VZ only, no? The exact parallel with the RL is VZ. So VZ will dictate the current through RL. Yes or no?
Yes, sir.
You just walk in the circuit in this loop, you will get the answer. So now there's the problem. What is the current through here? What is I1? Let's say I1 here. So how to find this I1? So walk in this circuit. How to write it? Question, guys? Vi minus I1R minus VZ equals to 0. Hello, hello, hello.
Yes,
In the loop one. So can I say I1 equals to Vi minus VZ by R? Hello, hello, hello.
yes, sir.
But they will ask you the third question. What is the current through the diode itself? What is IZ? So there is no formula for IZ, but because I know I1, I know IL, we can use the Kirchhoff's current law. So what is IZ, guys? I1 minus IL.
Yes, sir.
It is clear to all of you.
Yes, sir. Sometimes.
Yes, sir.
How to proceed with any zener question? It's very simple. First, you remove the diode. Step one is remove the diode. Solve the circuit. Check the V out. V out means the V which is parallel to the VZ. I mean the resistor which is parallel to the VZ. And then we have to solve. So now what we're going to do? We're going to solve question. All right. Let's go to the top one. Yeah, we have so many questions. This is okay. Start from here only. Question of 14 you can see. And you can do mentally. How to do mentally? Remove the zener. Remove it. Then okay, I'll show you how to solve mentally. Then R2 and R2 will be in parallel.
Sir.
So 1500, how much?
750.
750. 750 plus 500.
1050.
Or you can leave this. You know the voltage divider rule. 750 and 500 is 2 resistors. That's it. So 750 upon sum of the two, which is 1250 into 12. How much? 750 by 1250. 3 by 4, 3 by 5, no?
3 by 5.
3 by 5 into 12, how much?
$7.2, sir.
So 7.2 is less than 10.
Yes, sir.
So the zener is open circuit.
Yes, sir.
Yes, sir.
So current will be 0.
Yes, sir.
So option is A.
Yes, sir.
You
Yeah.
can check. You can check and tell me the answer. What is the answer given? I don't know. Okay. Can you see the answer, guys? Hello. I think it's the reverse. You have done the no, that's one. That's correct. What is the answer? A is the answer. Answer is on this same page. It's below. It's option A. So 0 only, no? Yeah. So mentally done. How many of you understood this calculation? If you know from current and electricity how to do the voltage divider and all, you can do mentally. But anyway, you can do by the rigorous calculation as you want. Question number 20. Let's do mentally. So remove the zener. We have only two resistors, 1500 and 500. What is the answer? What is the voltage across R2, guys? 15 by 20 into 15.
Yeah.
15 by
4.
20. 3 by 4, no?
11.25 around.
How much? It is more than 10.
Yes. 11.25.
So it means it is who will regulate the voltage?
The zener diode.
So R2 will have how much current? 10 by 1500. So 10 by 1.5 ampere milliampere. 10 by 1.5 milliampere. So 10 by 1.5 is how much?
6.7 D.
So that's the current through the current through R2. What the question?
R2.
The current through the zener is how much? Diode is how much? So we need to also find the current through
Current through the
the
loop.
R1 first. R1. So move in the outer circuit. 15 minus 10, which is 5. 5 by 500 is how much? 1 milliampere. 5 by 500 is how much? 5 by 500. 1 by 100. So it is, sorry, 10 milliampere, no? 10 milliampere.
Yeah.
So out of 10 milliampere, how much current is going through R2? 6.7. So how much will go from the zener diode? 3.3. Answer should be B answer. You can check and tell me. See, if you want, you can solve. I'm not saying don't solve. If you're not able to understand what I'm saying, do the calculation and get the answer. That's it. Is the answer B given, Rishi?
Sir, yes, sir.
Are you able to understand what I'm saying?
Yes, sir.
Yes.
Yeah.
You all are able to solve?
Yes.
Yes.
Okay, so solve few questions just to get confidence. Zener, yeah, everywhere zener. Solve this 13th question. 9th question also. That's very interesting. 9th seems to be an interesting question. Yeah. Solve 9th and 13th. So next week I'm going to also add three more lectures because yeah, I'm available. I'm here only. So we can add 3 more lectures next week also. And then I'm going to add 1 extra lecture to the semiconductor so that we can finish in detail with practice also. And I will add few lectures too. 1 lecture to the KTG and 1 lecture to the, yeah, I think EM extra.
Okay, sir.
Solve. It's easy. I mean, the thing which I have discussed is sufficient to solve, but anyway, see if you can do it. In the mains, you can expect mostly question from the diode only. Transistor may have a separate question. But in bit set, they ask 3 to 4 question only from the semiconductor. So anyway, it's a very good scoring chapter for bit set also and for mains also. And I think from this year, it is also part of advanced, right, guys?
Yeah, sir.
Then you need to, go deeper only. So for advanced, I will be sharing some more difficult question for practice. I know from which book they copy the question. So I'll share those questions from the book which I have. All are from the VTech textbook only. So since I have all those books at my home, I'll share. So these all questions are copied from that book only. I mean, the book which I have. The 3-4 books which are very famous.
Okay.
So 13 done.
So doing some.
Okay. Manav is here. Done, guys? Any question? 13 or 9?
13th one done, sir.
Okay, very good. So do it 9th.
Yes, sir.
So you're supposed to find the IZ, I think. Hmm. 12 minus 8 is 4. 4 by 400 is 10 milliampere. 10 milliampere. Is coming. And 10 will go from here. So 10 into it. Is it 80? I think it's 80 milliwatt something. 80 is answer. Let me see the option. Where is the answer? Okay, is it integer type answer? Okay, maybe. Yeah, tell me the answer for question 9. Receive. What is the answer?
1 second.
It should be 80 only. Parv, tell me, are you getting the answer?
Yes, sir. Just a second.
You got for 13 answer, 13?
Ha, sir. I tried first time, but and in the second try got.
Dash, you got the answer for 13?
Sir, 9th is 40.
That's 40. Okay, what we missed? 4 by 400. The input is, you're saying 14, no? 40, so that we missed.
Yeah.
Okay. Each diode is, total is 80, so each diode is 40. Is correct. They're asking the power through each diode. I got it for the entire diode. It's 80. That's correct. So you can get the answer easily. What is the current here? Current is 4 upon 400, right? Isn't it?
Yes.
And power formula is P equals to V into I. So we know the voltage across the each diode is 4 volt. So 4 into current, which is 10 milliamp, 10
Yeah.
milliamp. So that's it. All questions can do mentally. You have to use the P equals to VI formula. Whenever it is power of a diode. So if you know the current and if you know the forward resistance, you can do that way. If you know the voltage, then I into V. So for zener diode, the power is always VI because V is fixed in case of regulation. In forward bias, it is I square R because in the forward bias, what we have is
Forward resistance.
forward resistance. That's dynamic resistance, right? Okay, I think all are done. Do I need to explain any other question? 13 question. So let's do this question. So 8 seems to be nice. Can you solve 8 and 12 quickly? 8 and 12. Then I solve the next also. Solve 8 and 12 just based on the same idea. It is RC circuit with a diode. Okay. See, lecture is over. I'm not going to teach anything. I'm just going to practice. So if you want to practice, you can stay. If you want to go, you can take a rest also. It's too late now. So next class, I will start the optoelectronics devices and transistor. So next class, I should be able to finish 80% of transistor. 20% I'll take in some other lecture somewhere. And then there's a logic gate also. So that I will also cover with the. So I think 2 lectures will take, including logic gate and practice. Okay. Okay. Yeah. So we have lecture. What else?
Done, sir.
Done both? Okay. Very good.
Along with 8, which are different. 12.
8 and 12, yeah. 8 you got, na? 8 you got. Anybody else who got the 8th? Ashika, you got?
Sir, doing so.
Okay. Once you're done with the 8th and 12th, then solve 7th. This time pass, but solve 7th. It's a like based on the bridge rectifier, right? So you have to find the path which is,
Yes, sir.
that's it. And then again, I think this question 11th is similar to the all those junior question, right? All are same question. How many questions they ask? 19, 20 January to, oh my God. So in 2020, 9th January, there are 2 questions in the same shift or different shift. I don't know. Let me see the last question, whether they are asking more than one or only one. Okay. So one question I can see.
So after the 7th question,
After 7th, okay, you are done with the 12th, no?
yes, sir.
Solve 11th. All are same.
Okay,
Okay, just solve 11th. I think that is sufficient for today.
okay, sir.
And then if you can solve the remaining from the diode part, wherever you see diode, just attack it. Okay.
Yes, sir.
Yes, sir.
So I think now we can end the lecture. Let me see what is left. Okay, that's it. So there is also a very nice graph question. Yeah, question 3, just solve 3. It's very interesting. Which of the following graph is correct graph? Guess. in every half cycle, one of the diode will be forward bias, right?
Yeah.
Yes, sir.
That you can remove it, right? So you're left with you're always left with one reverse bias. And once you cross the V0, it will regulate the value, right? So you can easily guess the answer. Which is the right answer? Who
C.
will guess? Huh?
No, not C. One second.
The A, B, C, D. 4 options are there. Which option is correct?
C.
Yes,
C
C.
is the right answer. Correct. Logical, na? C.
Yes.
Less than V0. See, in any case, one is forward bias. The one who is reverse bias will not regulate, will act as open circuit if it is less than V0, right? So
Yeah.
the output will be same as the input.
Yes.
And then the moment you regulate, it become constant. So actual graph, flat, actual, flat, actual, flat. It's not, it's a wrong graph. It should be smoothly drawn, actually.
Sir, there should be a curve,
Yeah,
right,
yeah.
sir?
Yeah, that there must be curve, not so. There must be curve. So I think if that is exactly straight line, it's wrong graph.
Mm,
Hmm. Is the option given C?
I haven't checked. Sir.
Just check.
Sir, yes, sir.
No, I think they have drawn wrongly. I mean, the whoever guy, like whoever has drawn, that's wrong. Don't worry, that's wrong.
Yeah, sir, it's C.
I mean, the problem is with the graph. Let me show you the exact graph. It's a very famous question. So any textbook will give you this question always. Hmm. Yeah, I'll just show you. So you all can see it. Can you see the graph now?
So I cannot
Yes.
see the questions.
Pardon?
I cannot see the screen. I cannot see the graph.
I have shared one graph in this WhatsApp group.
Acha, okay.
Oh, it looks like very straight. It's not straight. It is actually curve graph.
Yes. Yes.
So this question is taken from this book. Okay, I have a book in which every question is solved. Anyway, so this is all right, guys. So I think that's sufficient. We have almost covered the 60%. This is one more question. This is a unique question. Let me do this. Yeah, 22. Can you solve 22? We have done today, na? This input output characteristic graph. What is the ratio of forward to reverse bias? Common sense. What should be the answer? Without solving. Forward is very, very small than reverse, right? Reverse is like infinitely large. It's in mega ohm. And forward is in ohm. So which option?
B.
B option. No, without solving, you can tell. Anyway, you can check. Maybe you need to solve this question in this case, but ideally that should answer. What is the answer? Hmm?
It's B.
B. No, that's logical. All right, so I hope you can do the rest of the question. There is a separate chapter for the logic gate. So they have given, I think. Logic gate is separate, right? There is that chapter. So after this chapter, this is the logic gate, yeah. And this is same chapter. This is, yeah, this is the next topic. Yeah, topic 2 is junction transistor. We have separate topic. Yeah, this question we have to solve. This will be slightly difficult, but anyway. And then we have logic gate, which you can solve very easily. So I will explain the logic gate. Logic gate will take 10 minutes to master. All right. Okay, guys, bye and take care. Good night.
Night, sir.
Thank you, sir.
Thank you,
Sir.
sir.
Bye, sir.
Thank you, sir. Bye, sir.
Bye bye.
सर
हम्म
सर वो आज सुबह हमने बात की थी ना वो कैलकुलस लेक्चर के बारे में, तो वीडियो टेक इट टुमारो.
Calculus. What exactly calculus? Tell me.
Sir, actually, me, Agar, and Archit weren't confident about the calculus part of maths. So if you could take a lecture tomorrow.
No, what you want to understand in that part? How to take elementary and or what? That
No, sir, the integration and
integration. Integration. See, come on. Integration you should learn in maths.
definite integration and that.
So that is you can learn in maths, and for physics based integration, I can just share the link. You can watch it. It's very easy. Have I shared those lectures? No. So there are 3-4 lectures which you will master you with elementary and integration. Okay. But still, if you have doubt after that, you can then ask. Because see, I cannot teach you the entire integration. It is a big topic. I mean, it requires a lot of ideas, a lot of practice. So if you want to master it, the only way is practice, practice, practice. If you're not okay with the basic, I can explain the basic part. Like if you don't understand what is definite integration, what is the meaning of area and the curve, that can be explained.
Sir, if that is okay.
Okay.
So,
Tomorrow I'll talk to you. I mean, tomorrow I'll tell you the schedule when we can discuss. Okay.
okay.
I'll share the videos. You watch the video. Let's see if it if it serves your purpose. If it is not, then I'll take some extra lecture. Okay.
Okay, sir.
Because don't waste time in learning this something really simple. Just remember the formula of basic integration and go next. Do something else. Integration is a huge chapter in mathematics. In maths, you all have covered the integration. Yes or no?
Yes, sir.
Yes.
No,
Yes.
that is sufficient. Then that is sufficient. See, anyway, I'm not going to teach you more than mathematics. I will teach maybe 1/10 or 1/20th part of maths, right? So what I need is simple, that I teach to the younger kids who coming from class 10 to 11. So they don't have the exposure of calculus. You guys having the exposure of calculus. So what I need to teach you guys, you have to first explain for me. Okay. But exactly this is what I want to learn. Then it will make it more meaningful. Randomly, if I start teaching integration, what does it mean? Like to explain what is area under the curve? Why dx? It's done. Nothing else is left actually. So you come with some more concrete, reason, like what is your difficulty, where you get stuck. And if you are getting stuck with the, I don't know what is the integration of sine theta, d theta, there's a set of formulas, just watch it. Come with some more concrete reason, like why you want to learn. What are the things which you are feeling it's difficult for you and you should know it again. So with more concise, requirement I can give you. Just if you say me that there's a wide, big space of integration, just teach integration. Then what I can teach? X power n dx is x power n plus 1 plus n plus 1. That's it. So those things are no use, no?
Yes, sir.
I mean, you just come with some more, sensible topic. Like I want to understand how to take elementary. There's a lecture I have taken on elementary. So you can watch those lectures. Exactly what we mean by elementary. Why we do integration in physics. So that lecture I have taken. What do we mean by volume? What do we mean by area? So that I have taken lecture. So I will be sharing those lectures. It's just 3-4 lectures. Watch it, you will come good with those ideas. If that is your requirement, it's easy. If something else, let me know.
Yes, sir. I'll talk to you about it tomorrow.
Yeah, tomorrow we can discuss. Don't worry.
Yes, sir.
Okay.
Thank you, sir.
All right, guys. Good night. Take care.
Sir,
Yeah.
I had sent you an optics doubt. I still didn't really get what you said there. Could you explain it?
Which one?
Sir, that about the
you send me the
tab
photograph.
yeah.
That medium wala.
Mm-hmm.
It's simply a medium thing. Right?
Huh.
Okay. So the mirror is one of the layer of the glass, right?
Yeah.
So mirror will look through the glass only, not through air, right?
Yes.
And if a person is here watching the object, he will not see the object here. He will see the object at a distance mu times d naught.
Yes.
So object will appear. Now this is like a entire, now object is captured in the mirror, right?
Mm-hmm.
So you're solving a question in a mirror itself, right? And distance is how much? Mu d naught. Because the object is at a distance mu d naught, so it will form the image here, right?
Yes.
So for any observer in the air, the answer is simple. How we write the answer? So the answer from this answer is how much? Twice mu d naught. So that upon medium of the glass equals to person upon medium of the person, right?
Which is 1. So it shouldn't make a difference. Right?
So medium of the person is what?
Air. Observer, right?
Observer. Mu of the
Observer is an air.
So observer is the air, right?
Hmm.
So this is the answer as by the mirror. Mirror will see the object there and mirror will form the image here. Okay.
Mirror will see it
Now,
at mu d.
Yeah. So this we have to take only this part. This is the part, right? Mirror is forming image here, right? So from this edge, how far is the image in the mirror frame?
Mu D
mu
naught.
d naught. Okay. Oh, that's it. So what we are asking for?
Sir, because in the lecture you had taken something else only. In the lecture, you had drawn it as if there was a air gap in between the glass slab and the mirror.
That is called the method of interface. It is not drawn. It's like you can understand the two things. The role of the slab is to shift the graph, right?
Yes.
Shift the object. So if object is actually here and the mirror is on this side, there is no gap. Then it will appear here actually. And this is equivalent of the normal shift.
Sir, but shouldn't the object appear behind the, like, apparent object be behind the real object? Because that's what we saw in the last method.
No. When the light ray will go this direction.
Huh.
So for incident ray, the object shifts in the incident ray direction.
Okay.
While coming, it will shift backward. So while coming, so now what is the distance now left with? The actual distance minus delta here.
D minus delta.
And then it will form the image on the same side on this way.
Huh.
But again, we have to make a shift. So while coming, the light ray will, because see, you will not see this object, you will see the reflected light, right?
Okay. Yes.
So this will further shift by delta n. So this is the answer from here, and then shift by delta n. What is the left answer?
D.
2 delta n.
Third D.
The delta n, this is complete, no? So if you go back by delta n, then you are having the d minus 2 delta n, the actual distance.
Yes.
So this is how I have solved. I think I have solved by 3 methods. I mean, if you
Yeah,
watch,
3 methods.
if you watch it, just stick to the easy one. Shift the mirror, solve the question. That's it.
Sir, so isn't this method giving a different answer than the last?
No. All will give same answer. You can see the lecture. Every method will come
Can
to
you
the
show the
same.
last slide once?
I need to check actually. I haven't seen them for a long while.
Maybe the last slide which you just solved right now. इसके पहले वाला. जो. अच्छा.
So I removed it.
अच्छा, okay.
No, in
You
last also you will get the same answer. I mean, see,
उसमें
you can
delta
see
n
this
का term नहीं आया था. It was just the
one.
same
No,
as.
no. So I haven't taken the shift, no, in that question.
The shift isn't necessary in that question. Like,
No.
दोनों में
Then,
shift ले भी लिया और निकाल भी दिया, but
no, shift
distance
is not
करना
required. What I'm doing here is I am looking at the apparent position of object. So the question is, I mean, must be some question.
The question is, find the distance of image with respect to observer. Observer is at d distance from the slab.
And this is H
T.
or T, whatever. Okay, this is T and this is D, correct?
Yes.
So first of all, you need to understand that, okay, who is the observer here? The person is the person is observer.
Yeah.
So first of all, we are doing the reverse process. We are trying to solve the question in the mirror frame.
Okay.
So mirror will see the object mu d plus t, right? T plus mu d, na? So T plus mu d this side.
पीछे shift over.
So it will form the image same here, T plus mu d.
Yes. But we'll shift it again ahead.
And so the distance of the so how far is the distance from the observer actually? So what is the distance of the?
At first we'll remove we'll have to shift this also back, right? Because this mu
No,
d is
don't shift. It's not just divide by the mu to get in the answer of air.
Okay.
That's it. So it will become how much? I think T by mu, right? It is 2T by mu plus a D. So what's the answer? The right now the answer is, so for mirror it is T plus mu D, isn't it?
Yeah.
Yes, then you have some doubt?
Yeah, I wanted to ask if like I could understand about Schrodinger's a bit right now, or we could do it some other time as well.
We can do it some other time, maybe tomorrow. So Ranjay question is basically a probability distribution curve.
Mm.
So what you draw is the probability distribution. It is not something cloud or something wave. Okay.
No.
And that is the graph drawn in the polar coordinate system, in the spherical coordinate system. Okay.
Hmm.
So it's a polar graph. So you're not supposed to go deeper into the exact nature of graph. It's a polar graph drawn in 3 dimensions. So you can go to some maybe a calculator which can do the polar graph. So you just stick to the idea that okay, these are the shape which you're supposed to remember. That's it.
I'll just share the kind of questions I was facing problem and then maybe you can guide me.
Just share with me. I mean, I'll see it.
Yeah,
Okay.
okay. Thank you, sir.
So this is T plus mu D, because the mirror will see the object here. Okay, this is a mirror observation. Mirror will see the object there and so to form the image there. Okay. And but we want to convert this answer in the ground frame. I mean the air frame.
Yeah, because we are also
So-
seeing through the slab, so हमारे लिए भी पीछे shift हो जाएगा.
So to do this, this is simple. I mean, we just need to divide by the medium only, nothing else. So for mirror, the answer is T plus mu D. Okay, what we are missing here? T plus mu D, T plus mu D. And we get the answer from interface only. So from this interface, how far is the object? From the interface,
2T
where
plus
things
mu.
are changing. 2T plus mu D, right?
In the mirror frame.
In the mirror frame. So in the ground frame, it will be this much. Plus D extra.
Because observer.
So
2T by mu plus 2D.
let's do this one. D minus
T. फिर ऊपर वाले में D और T अलग ले लिया था ना हमने. Like
नहीं वो तो ठीक है. हाँ गलत कह रहा है. D plus T हो जाएगा T plus D minus delta. तो कट गया है तो ये T देखो. ये 2T चला गया, D चला गया. सेम है ना सर.
ओके.
वो तो सेम ही आना चाहिए. आंसर अलग नहीं होगा.
नहीं, मुझे एक्चुअली कंफ्यूजन हो क्योंकि दोनों में एक में ऑब्जेक्ट पीछे शिफ्ट हो रहा था और एक में आगे शिफ्ट हो रहा था. तो
वो देखो वो कैसा है ना कि इट डिपेंड्स ऑन कि हाउ आई एम टेकिंग द फ्रेम. So the same question can be solved in variety of frame. Like if I want to perceive first from the mirror frame, then shifting to the air, or I'm directly shifting the mirror because of slab.
Okay.
See, the role of any slab is to shift. So once you shift, then the role of slab is gone.
Okay.
Then solve the question as if there is no slab.
Okay.
So for incident direction, the shifting of the object is, so the mirror will perceive O dash. Because the image formation by the mirror depends on where it will perceive the object.
Okay. Yes.
Not the reality. So mirror will perceive object to be at O dash. Will form the image, but when the light will reflect back and coming towards the observer, in the coming process, it will
again
further
pass
shift.
through the slab.
So again, the incoming light ray will be shifted by the slab again.
हाँ.
So whenever is the answer, I have to shift that answer by again delta n to get the actual answer.
Understood. समझा.
कितने लेक्चर हो गए तुम्हारे? How many lecture finished?
ये कौन सा